This means that the mirrors are positioned so that when the light from the two arms recombines at the beam splitter, the light waves are exactly out of phase. The peaks of one wave align with the troughs of the other, and they cancel each other out perfectly.
So if you look at the output port where the detector is, it's pitch black. No light escapes.
Exactly. Because energy has to go somewhere, all that laser light is reflected directly back toward the laser source. Now, in a basic setup, that reflected light is just wasted. But in power recycling, they place a highly reflective mirror, the power recycling mirror, or PRM, between the laser and the beam splitter.
Ah, so the light tries to leave, hits the PRM, and gets bounced back into the machine.
Right. It creates an echo chamber. The laser light gets trapped between the power recycling mirror and the Fabry-Perot arms, building up more and more intensity. That is how they boost a 200-watt input laser up to a massive circulating power.
Okay, that makes sense.
Yeah.
But the dual and do recycling means they added a second recycling mirror for advanced LEGO, the signal recycling mirror, or SRM. Where does that go?
The SRM is placed at the output port, the dark port, where the gravitational wave signal would eventually exit to hit the photodiode. By placing a mirror there, they create a new resonant cavity called the signal recycling cavity. And this mirror completely changes the quantum dynamics of how the detector operates.
How so? The sources get really heavy into phase modulation and something called resonant sideband extraction.
Let's break that down. When a gravitational wave passes through the detector, it stretches one arm and squeezes the other. This microscopic change in length subtly shifts the phase of the laser light inside the arms.
It knocks it out of that perfect cancellation alignment.
Yes. And in optics, when you phase modulate a carrier wave, you create what are called sidebands. These are new frequencies of light, slightly higher and lower than the main laser frequency. The information about the gravitational wave, the actual signal, is carried entirely by these sidebands.
So the main laser is the carrier, and the wobble is the sideband.
Exactly. Now remember those Fabry-Perot cavities in the arms? They are designed to trap the carrier light for a long time, hundreds of bounces to build up power.
Right.
But if the signal sidebands stay trapped in the arms for hundreds of bounces, you have a problem. If a high-frequency gravitational wave comes through, and the arms change length very quickly, the sidebands bouncing back and forth can actually get out of sync with the gravitational wave itself, and they start to cancel each other out.
Oh, I see. You want the main laser to stay trapped, but you want the delicate signal to get out as fast as possible before it gets scrambled.
Precisely. And that is what the signal recycling mirror does. By acting in concert with the arm cavities, the SRM allows the scientists to decouple the storage time of the carrier light from the storage time of the signal sidebands. By manipulating the microscopic position of this mirror, they can effectively extract those high-frequency signal sidebands from the arms much more quickly. This is resonant sideband extraction.
I think an acoustic analogy works really well here. Think about an acoustic guitar, right? If you just take a guitar string and stretch it tight between two metal posts in the open air and pluck it, it's not very loud. And you can't really shape the tone. The string vibrates, but that's it.
Right, there is no resonance.
But when you attach that string to the wooden body of a guitar, the body acts as a resonance chamber. It takes the vibration, the signal, and amplifies it. And a skilled luthier can design the exact shape of that chamber to emphasize the deep bass notes or to emphasize the bright treble notes.
That is a phenomenal analogy. The signal recycling cavity is the body of the guitar. By physically moving the signal recycling mirror by fractions of a wavelength, the scientists can actually change the shape of the detector's quantum sensitivity curve.
They can tune it.
They can literally tune the detector like turning a dial on a radio. If they want to listen for the heavy, low-frequency in spiral of two massive black holes, they tune the SRM one way. If they want to optimize for the high-frequency chirp of two neutron stars colliding, they tune it another way.
But wait a minute. How do they move this mirror? We just spent the first 20 minutes of this deep dive talking about how these mirrors are hanging from 4 stages of glass threads inside a hard vacuum, and we can't touch them or we ruin the seismic isolation. How do you tune a mirror by fractions of a wavelength if you can't reach in with a wrench?
You use an electrostatic drive, or ESD?
Electrostatic, like static electricity.
Exactly like static electricity. Have you ever rubbed a balloon on your hair and used it to pick up little pieces of paper?
Sure, yeah.
You are creating an electric field that induces a dipole in the paper, attracting it to the balloon without needing any physical strings or glue. Advanced LIGO uses the same physics, but with breathtaking precision.
How does that look in the machine?
Behind the test mass mirror, hanging on a completely separate parallel pendulum chain called the reaction chain is a reaction mass. On the face of this reaction mass, there is a complex pattern of gold electrodes.
Oh, I see where this is going.
The test mass mirror is made of fused silica, which is a dielectric material and insulator. By applying a very specific voltage to the gold electrodes on the reaction mass, they create a fringing electric field. This field reaches across the small gap and interacts with the molecules of the glass mirror via dipole interactions.
They use a static charge to gently pull on the glass block.
Yes, it allows them to apply incredibly precise, ultra-low noise forces to the mirror without ever physically touching it. There are no wires connecting them, no mechanical links to transmit vibration. The suspension thermal noise remains pristine, but they can still make the microscopic adjustments necessary to lock all these complex optical cavities into perfect resonance.
It's just staggering. Okay, so all these mirrors are locked. The laser is humming at 830 kilowatts, the Earth's vibrations are neutralized, and a gravitational wave comes through, stretches the arm, and creates a signal sideband. How do we actually read that signal out of the machine? The sources mentioned they changed the readout method for advanced LEGO. They moved from RF readout to DC readout, and they added an output mode cleaner.
Right. In initial LEGO, they used radio frequency phase modulation to read the signal. It worked, but it introduced extra quantum noise. For advanced LEGO, because they had so much more laser power, they shifted to a DC or homodyne readout.
What does homodyne mean in plain English?
It means they intentionally unbalanced the interferometer just a tiny bit. Instead of tuning it to a perfect pitch-black dark fringe at the output port, they offset the mirrors by a few picometers.
A picometer, so a trillionth of a meter.
Yes, just enough so that a tiny, highly stable amount of the main carrier light leaks out of the dark port all the time.
So the detector isn't looking at total darkness, it's looking at a very faint, steady glow.
Correct. This leaked carrier light acts as a local oscillator. When a gravitational wave passes through and generates a signal sideband, that sideband exits the detector and physically beats against the steady local oscillator light. This interference creates a variation in the intensity of the light. It makes the glow flicker, and that flicker is what the photodiode measures.
But before that light hits the photodiode, it has to go through this output mode cleaner. Why? Isn't the light coming out already pure laser light?
Unfortunately, no. Despite all the super polishing and the active thermal compensation, the optics are never perfect. There are microscopic misalignments and tiny thermal defects. These imperfections cause some of the laser light to scatter into higher-order spatial modes.
What is a spatial mode?
Think of the shape of the laser beam on a wall. A perfect fundamental mode called the TEM0 mode looks like a perfect, clean, solid circle of light. But higher-order modes look messy. They might look like a donut or cloverleaf or two splattered dots side by side.
Oh, okay, so the messy light is carrying the thermal defects.
Right, and this junk light carries absolutely no information about the gravitational wave. But if it hits the photodiode, it still contributes to the quantum shot noise. It adds hiss without adding signal.
So you have to get rid of it.
Exactly, so they built the output mode cleaner. It is a small, rigid, extremely precise optical cavity placed right before the photodiode. It is designed to be resonant only with the perfect fundamental TEM0 mode.
So it acts as a physical filter, the perfect round dot of light passes straight through, and the messy cloverleaf light gets bounced away.
Exactly. It filters out all the optical garbage, ensuring that only the purest carrier light and the pure gravitational wave signal reach the detector, giving them the lowest possible noise floor.
Okay, let's just take a breath and synthesize this. We have built an L-shaped vacuum tube 4 kilometers long. We have actively isolated the platforms from ocean waves hundreds of miles away using hydraulic noise canceling. We've hung perfectly polished 40-kilogram glass blocks on welded glass threads to eliminate atomic friction. We are pumping nearly a megawatt of laser power into them, fighting the heat distortion with precision ring heaters, tuning the quantum sensitivity with static electricity, and filtering the output light through a dedicated mode cleaner. The physical hardware is an absolute masterpiece of extreme engineering.
It's almost hard to believe it's real.
Right. And out of the end of all this effort comes a signal on a computer screen. A tiny, faint variation in light intensity. A squiggle on a graph.
A squiggle buried in whatever residual noise the machine couldn't filter out.
Right. And here's where we hit the final, crucial phase of our deep dive. Decoding the cosmos. Because having the hardware is really only half the battle. If you see a wobble on your graph, how do you know if it's two black holes colliding a billion light years away, or a glitch in the thermal compensation, or a microscopic dust particle falling through the laser beam.
The hardware is blind without the software. You need a template. You need to know exactly mathematically what a black hole collision should look like so you can run a matched filter and search the noisy data for that exact shape.
And this leads us to the theoretical physics papers in our stack. Now, my naive thought was we have Einstein's equations of general relativity, right? They describe gravity. Why can't we just program the masses of two black holes into a supercomputer, press enter, and have it spit out the waveform?
If only it were that simple. General relativity is famously nonlinear. The mathematics are chaotic, especially when you get into strong field regimes. This raises an important question: how do we calculate the chaotic merger without crashing our computers?
What makes it so nonlinear? In Newton's gravity, you just calculate the force between object A and object B, right?
Yes, Newtonian gravity is linear. The gravitational field is just a force in a fixed background of space. But in general relativity, gravity isn't a force, it's the curvature of space-time itself. Mass curves space-time, and curved space-time tells mass how to move.
Okay, follow you.
But here's the catch. The gravitational energy itself also has mass equivalence. E equals mc squared, which means the gravitational field creates its own gravity.
Gravity gravitates.
Exactly. The equations feed back into themselves infinitely. When two black holes are far apart, moving relatively slowly, we can handle this using an approximation technique called the post-Newtonia, or PN expansion.
I saw this in the sources, the PN expansion, the 1PN, 2PN, 3PN terms. What exactly are they doing?
It's a way of slowly adding relativistic corrections to basic Newtonian physics. You assume gravity is mostly weak, and the speeds are much slower than the speed of light. You take the Newtonian answer, and you add a small mathematical correction based on the ratio of their velocity to the speed of light, v over c. That's the 1PN term.
Right.
Then you add an even smaller correction for the next order of complexity, the 2PN term.
It's kind of like calculating the tip on a dinner bill. You figure out the 15%, and then you add a few pennies to round it up perfectly.
That's a good way to look at it. The post-Newtonian Hamiltonian, which is just the equation describing the total energy of this two-body system, works beautifully while the black holes are slowly spiraling toward each other over millions of years. But as they get closer, their speeds approach the speed of light, and the gravity becomes incredibly intense.
The v over c fraction is no longer small.
Right. The post-Newtonian approximation starts to completely break down. You need more and more complex PN terms, 3PN, 4PN, 5PN, and the mathematics become wildly unstable. If you just try to feed these equations into a supercomputer to simulate the final plunge, the computer will crash, or it will take months to calculate just a few seconds of the merger.
So if the math breaks down right when the black holes are about to collide, which is the loudest part of the signal we want to hear, how do we solve it? Wait, the sources talk about a mathematical framework called the effective one-body, or EOB.
I tried reading this paper and I got totally lost.
It's heavy stuff.
Yeah, they talk about a canonical transformation to map a two-body problem onto a one-body problem. How can you just pretend two massive spinning black holes are actually just one object? That feels like cheating.
It's not cheating. It is one of the most elegant mathematical tricks in modern theoretical physics. The EOB approach recognizes that trying to track two massive, complex bodies non-linearly interacting with each other is computationally impossible. So they apply a canonical transformation in phase space. Okay, stop right there. Phase space. Canonical transformation. I need an analogy here because the math is way too abstract. Let's try this. Imagine you are a meteorologist trying to track two complex, powerful tornadoes that are circling each other, interacting and preparing to merge. Okay. Tracking the wind speeds, the pressure changes, the temperature gradients of both chaotic systems simultaneously, and how they affect each other is mathematically impossible, right?
A very apt description of the binary black hole problem. The feedback loops between the two tornadoes would just overwhelm any model.
Right. So instead of trying to model two tornadoes, what if we use a mathematical trick to essentially freeze one of the tornadoes? What if we take all the mass, all the wind speed, all the complexity of tornado A and tornado B, and we bake it into the landscape itself? We warp the ground and the atmosphere to represent all that chaotic energy.
I like where this is going.
And then we treat the remaining system as just a single simple point, an effective body moving through that highly warped, deformed landscape.
That is precisely what the EOB mapping does. You've hit the nail on the head. In the mathematical physics, they take the real post-Newtonian Hamiltonian, which models two distinct masses, m1 and m2, moving through flat space, and they use these reduced variables, p and q, to map it onto an effective Hamiltonian.
The effective body moving through the deformed landscape.
Yes. The effective body is a single particle with a specific reduced mass, which is calculated as m1 times m2 divided by the total mass. And the landscape it moves through is a deformed metric, very similar to the Schwarzschild metric of stationary black hole, but tweaked with specific coefficients to account for the energy of the second body.
Wow.
It simplifies an impossible two-body problem into a highly solvable one-body problem moving through curved space without losing physical accuracy.
That is brilliant. You freeze the complexity into the background, and once they have this EOB Hamiltonian, what does it let them do?
It allows them to calculate things that the post-Newtonian expansion couldn't handle. Crucially, it allows them to calculate the exact radius of the innermost stable circular orbit, or ISCO.
ISCO. The point of no return.
Exactly. It's the orbital distance at which the black hole can no longer maintain a steady spiral. Once they cross the ISCO, gravity overwhelms their angular momentum, and they plunge directly into each other. The PN expansion fails at the ISCO, but the EOB framework remains mathematically stable right through the plunge.
So EOB bridges the gap. It takes the slow and spiral math, carries it smoothly through the chaotic plunge, and allows them to link it up with the massive numerical relativity simulations of the final merger and ringdown.
Precisely. It allows physicists to generate a complete, continuous analytical waveform template from start to finish, and they calculate millions of these templates for different combinations of black hole masses and spins. Without this massive library of EOB templates, advanced LEGO would just be recording static. It wouldn't know a black hole from a passing truck.
But the theoretical physics in these sources goes even one step further, touching on something called post-Minkowskian, or 1 p.m. scattering. This seems different from post-Newtonian. What is the distinction here?
It's about what you are trying to approximate. We said post-Newtonian assumes weak gravity and slow speeds. But what if you have a system where the bodies are moving incredibly fast, close to the speed of light, but they aren't bound in orbit?
Like two black holes that aren't orbiting, but just flying past each other in deep space.
Exactly. A scattering event. For that, you use the post-Minkowskian approximation. It assumes weak gravity, meaning the black holes are far enough apart that their gravity is just a small perturbation on flat Minkowski spacetime, but it makes no assumptions about speed. It works for any velocity, all the way up to the speed of light.
So it's exact in velocity, but approximate in gravity.
Right. The 1 p.m. math linearizes the flat space-time perturbations to calculate the scattering angle, basically how much the black holes deflect off each other's gravitational pull as they zoom past. Now, you might wonder why we care about scattering black holes when LEGO is looking for orbiting, merging black holes.
Right, I was just thinking that scattering black holes wouldn't produce a sustained gravitational wave that we could easily detect.
True. But the sources reveal a deep, fundamental connection. There is a mathematical EOB energy map that demonstrates a direct correspondence between unbound scattering systems and bound orbiting systems.
Wait, meaning the math that describes two black holes flying past each other can be mapped directly onto the math of two black holes orbiting each other.
Precisely. Because the underlying gravitational interaction is the same, physicists can calculate highly complex relativistic interactions in the much simpler scattering scenario, extract the critical coefficients, and map them directly back into the EOB Hamiltonian for orbiting black holes. It's a shortcut to making the templates even more accurate.
That is a stunning synthesis. They're using the physics of a near miss to perfect the math of a collision.
It's the pinnacle of theoretical modeling, and it is the invisible software that makes the incredible hardware of advanced LIGO actually function as an observatory.
Okay, this has been an absolute marathon of a deep dive. We started with the sheer audacity of trying to improve an instrument by a factor of 10, unlocking 1,000 times more of the universe. We explored the active hydraulic shock absorbers fighting the ocean waves and the passive quadruple pendulums hung by welded glass threads.
So much engineering.
Yeah, we talked about pumping a megawatt of laser power into atomic perfect supermirrors, fighting the thermal expansion with edge heaters, and tuning the quantum sensitivity with static electricity. And finally, we broke down the profound theoretical physics, mapping chaotic two-body collisions into effective one-body templates, just so we can recognize the signal and the noise.
It truly is the ultimate marriage of atomic-level engineering and mind-bending theoretical physics. Every single discipline of science had to be pushed to its absolute limit to make this machine work.
It is a triumph of human ingenuity. We've built an instrument so sensitive, It feels the tides of the Earth and the quantum jitter of light. And we've paired it with mathematical models capable of untangling the chaotic geometry of merging black holes. It's a machine that forces us to realize we are part of an open system, intimately connected to the violent, invisible tremors of the entire universe.
And the most exciting part is, advanced LIGO is just the beginning. We are only just starting to listen to the dark side of the universe.
Which brings me to a final thought for you to ponder. If this 10x upgrade to advanced LIGO allowed us to hear black holes merging billions of light years away, what happens when the next generation of detectors pushes this even further? We've used this current technology to map the violent deaths of stars and black holes in the modern universe. But eventually, with even better theoretical math, even colder and quieter mirrors, and perhaps even larger facilities stretching for tens of kilometers, we might just be able to tune our signal recycling mirrors to hear something much older.
Something much, much older.
Not the death of a star, but the very first fraction of a second of the Big Bang itself. The ultimate, primordial gravitational wave echoing from the dawn of time. Just let that sink in. What did the universe sound like at the exact moment of its birth? Because of the groundwork laid by the engineers and physicists of advanced LIGO, we might actually live to hear it.
You know, usually when we think about building something massive, like a skyscraper or a hydroelectric dam or even a miles-long suspension bridge,
Right.
we just expect the engineering blueprints to be all about, brute force.
Yeah, absolutely.
Like thousands of tons of steel, massive concrete anchors driven deep into the bedrock, and everything just bolted down as tightly as physically possible.
Right, because traditional mega engineering is all about resisting the chaotic environment through sheer, rigid strength.
Right.
You want your structure locked to the earth so that it doesn't move when the wind blows or when the ground shakes.
Exactly. But then you look at the engineering behind measuring gravitational waves, and it is just the complete and utter opposite.
It really is.
I mean, you're this gigantic 4-kilometer-long machine, but instead of locking everything down rigidly to the bedrock, you are practically suspending the most critical components in midair.
Right, yeah.
You're actively trying to isolate this machine from the rest of the universe just so you can feel a vibration that is, get this, smaller than a single proton.
It's deeply counterintuitive. I mean, to measure the most violent, catastrophic events in the entire cosmos.
Like black holes colliding millions of light years away.
Exactly, these events that literally warp the fabric of space and time. To measure that, you have to engineer the absolute quietest place on Earth.
Wow.
The detector just has to be deaf to the local world so it can actually hear the distant universe.
And that brings us to the core of today's deep dive. If you're listening to this and wondering how humanity actually pulls it off, well, you're in the right place.
For sure.
Today, our mission is to unpack this seriously dense stack of scientific documentation, architectural blueprints, and theoretical physics papers.
We are diving deep into the incredible technological upgrades that define advanced LIGO.
Which is, just to be clear, the second generation of the Laser Interferometer Gravitational Wave Observatory.
Right. And for those tracking the geography, there are two of these identical detectors operating in tandem.
One in the high desert of Hanford, Washington.
Yep. And the other one is in the pine forest of Livingston, Louisiana.
Right.
And the upgrades we are analyzing today, they represent a monumental leap in our observational capabilities.
Let's set the baseline for exactly why we needed an advanced LIGO in the first place. Because initial LIGO, the first generation, it proved the fundamental concept of a massive laser interferometer actually worked.
Right, it was a proof of concept, essentially.
But this upgrade, the second generation, it was always part of the long-term master plan. So what were the actual stakes for tearing apart a working machine and totally rebuilding it?
Well, the stakes were quite literally astronomical.
Okay.
The primary driving goal of advanced LIGO was to provide a factor of 10 increase in strain sensitivity over initial LIGO.
A factor of 10?
Yeah. Now, to a casual observer, a factor of 10 might just sound like, a nice incremental improvement.
Right, like going from an iPhone 10 to an 11 or something.
Exactly. But you have to think about what that means in three-dimensional space. The volume of the observable universe that the detector can probe, it scales as the cube of its sensitivity.
Right, because you aren't just looking down a narrow telescope tube. You are reaching out in every direction simultaneously. Like the detector's reach is a sphere.
Precisely. The volume of a sphere is proportional to the radius cubed. So if you can see 10 times farther out into the universe, your radius increases by 10.
And 10 cubed is 1,000.
Exactly. This upgrade translates to an enormous 1,000 times increase in the volume of space we are listening to,
Wow.
which means a 1,000-fold increase in the number of potential astrophysical sources that the instrument can detect.
That is just a staggering leap. I mean, we are talking about events like binary neutron star in spirals or massive black hole collisions. A 1,000-fold increase takes gravitational wave detection from being this rare, once-in-a-lifetime anomaly to, like, a routine observational science.
Right. We're talking about catching dozens of complex binary coalescent sources every single year.
That's amazing.
Exactly. It completely shifts the paradigm from can we detect this to we are now cataloging the invisible universe.
But to get that 1,000-fold increase in detections, the engineering team had to conquer the fundamental limits of physics. And I don't use the word fundamental lightly here.
No, definitely not.
We are talking about catching waves that alter the distance between 2 points by a fraction of 1,000th the diameter of a proton.
Yeah.
That is 10 to the negative 18th meters. It's hard to even wrap your head around.
It really is.
So to understand how they achieved this, we're going to follow the path of the laser. We'll look at the exact mechanics of how the light is manipulated, the material science of how the mirrors are forged, and how the team actually wrestles with the laws of quantum mechanics to pull this off.
It is a phenomenal journey through applied physics.
Sure.
And it all starts with a foundational architecture, which is essentially building a bigger light trap.
Okay, let's dive into the optical configuration. I think most people who follow astrophysics understand the basic core of LEGO is a Michelson interferometer. You take a laser beam, you hit a beam splitter, and you send the light down 2 perpendicular arms. The light bounces off mirrors at the ends of those arms, comes back, and recombines.
Yeah, that's the basic setup.
And if a gravitational wave rolls through Earth, it stretches space-time in one direction and squeezes it in the other.
Which means one arm gets slightly longer and the other gets slightly shorter.
Right. Because the arms change length, the light waves returning from those arms fall out of sync with each other.
Exactly.
They interfere, and you get a flickering signal at your photodetector. Now, the arms at Hanford and Livingston are physically 4 kilometers long, which, sounds huge for a vacuum tube.
It is huge.
But the sources point out that for this level of precision, 4 kilometers actually isn't anywhere near long enough.
No, not at all. 4 kilometers is practically microscopic when you're looking for strains on the scale of 10 to the negative 21st.
Really?
Yeah, to understand why, you have to look at the time the light spends in the arm. In Michelson's original 19th century interferometer, the light only traveled a few meters. But to get the sensitivity LIGO needs, the light has to interact with the gravitational wave for a much longer period of time as the wave passes through the Earth.
Because the wave takes time to wash over the planet.
Exactly. If the light just travels 4 kilometers and comes right back, it's out of the arm before the gravitational wave has even finished changing the space.
Oh, I see. So you need the light to linger in the arms.
Right.
And to do that, they use something called Fabry-Perot cavities.
Exactly. You place a highly reflective mirror, they call it the input test mass at the very beginning of the 4-kilometer arm, and another mirror, the end test mass, at the far end.
Okay, 2 mirrors.
Right. The laser light enters through the input mirror, but because of the specific optical coatings, it gets trapped.
Trapped.
Yeah, it bounces back and forth between these 2 mirrors hundreds of times before it finally leaks back out to recombine.
So it's essentially an optical echo chamber.
That's a great way to put it. It's a macroscopic optical resonator. By doing this, they increase the effective distance the light travels from a mere 4 kilometers to about 1,200 kilometers.
1,200 kilometers.
Yep.
That's a fascinating optical trick.
Yeah.
You fold 1,200 kilometers of laser path into a 4-kilometer vacuum tube.
It's brilliant.
But let's talk about the laser itself, because they don't just use a laser pointer. The documentation specifies a continuous ND.YAG 1064 nanometer laser. Why that specific laser?
Well, the choice of a neodymium-doped yttrium aluminum garnet, or ND-YAG laser, operating at 10,064 nanometers. It's highly intentional.
Okay.
First, 10,064 nanometers is in the infrared spectrum. This specific wavelength interacts very favorably with the fused silica glass used for the mirrors.
Favorably how?
It exhibits incredibly low absorption in that material, so it doesn't heat the glass up as much.
Okay.
Second, solid-state ND-YAG lasers can be engineered to be extraordinarily stable. They run in a continuous wave rather than pulsing.
And why is continuous important?
Because any fluctuation in the laser's intensity or frequency, even a tiny one, would look exactly like a gravitational wave to the detector.
Oh, right. You get false alarms constantly.
Exactly.
So you start with this incredibly stable, pure infrared continuous laser. But making the path 1,200 kilometers long is only half the battle. The physics dictating sensitivity also demands more light.
Yes, much more light.
More photons continuously measuring the mirror positions makes the detector more sensitive, which brings us to the concept of power recycling.
Yes. This is a feature they actually utilized in initial LIGO, but they significantly upgraded it for advanced LIGO.
Okay.
They introduced a specific optic called a power recycling mirror, or PRM, located between the initial laser source and the main beam splitter.
And what does that do?
Well, to understand why this is necessary, you have to look at the dark fringe.
Right, let's unpack the dark fringe because it's the whole reason the machine works.
Yeah.
When the interferometer is perfectly tuned and there are no gravitational waves, the light coming back from the two arms destructively interferes perfectly at the output port.
Right. The peaks of the light waves from one arm exactly cancel out the troughs from the other arm.
So the photodetector at the output port sees pure darkness, a dark fringe.
Exactly.
But conservation of energy dictates that the light has to go somewhere, right? It can't just vanish. If it's canceling out at the detector, it is actually constructively interfering in the other direction, straight back toward the laser source.
Exactly.
So without a recycling mirror, all this perfectly good, highly stabilized laser light just bounces out of the interferometer and is totally wasted.
Exactly. The power recycling mirror catches that returning light and reflects it right back into the interferometer, perfectly in phase with the new light continuously coming from the laser.
I read about this and it blew my mind. The initial laser input going into the system from the pre-stabilized laser is somewhere between 40 to 125 watts. But because of this recycling cavity trapping the light and forcing it to build up, the effective laser power circulating inside those 4-kilometer Fabry-Perot arms is boosted up to roughly 750 kilowatts.
It's a staggering buildup of optical energy. It acts as a massive resonance chamber for the carrier light.
I have to pause here, though.
Sure.
If you need 750 kilowatts of laser power circulating in the arms to get the sensitivity you want, why not just build a 750 kilowatt laser from scratch?
That's a fair question.
I mean, we have industrial lasers that powerful. Why bother with the complexity of recycling a 40-watt beam?
It's a logical question, but it really comes down to the brutal realities of thermal dynamics and spatial mode quality.
Okay, what does that mean?
Well, a raw 750 kilowatt continuous wave laser is not a delicate scientific instrument. It is an industrial cutting tool.
Right, it melts metal.
Exactly. It would be a terrifying piece of machinery. The thermal noise generated by the laser itself, the wild intensity fluctuations, and the sheer physical destruction it would cause to the initial optics would be entirely unmanageable.
So the beam wouldn't be clean, it would be jittery and messy, and you need this light to be perfectly smooth.
Exactly. You need the light to be in a perfect, fundamental Gaussian mode, what physicists call TEM00.
Okay.
By starting with a highly stabilized, meticulously controlled 40-watt laser, you guarantee the purity of the beam. Then, by trapping that pure light in a resonant cavity, you scale up the power without scaling up the raw noise of an industrial laser engine.
I think of it like a light savings account.
Oh, I like that.
Yeah, like if you deposit a small amount of money, or in this case, a small clean stream of continuous 40-watt light, and you never ever make a withdrawal, compound interest takes over.
That is an exceptionally accurate analogy.
The light just builds and builds on itself until you have a circulating wealth of 750 kilowatts.
Exactly. You are building up massive resonant power through perfect conservation.
Right.
But advanced LIGO didn't just stop at power recycling. That was just the front door. For the upgrade, they introduced a brand new suspended optic at the back door, at the asymmetric output port where the dark fringe is.
And what's this one called?
This is called the Signal Recycling Mirror, or SRM.
So we have dual recycling now, power recycling at the input, signal recycling at the output.
Yes.
I understand why we recycle the power, but what exactly is the signal recycling mirror doing?
To understand the SRM, we have to look deeper at what a gravitational wave actually does to the light.
Okay.
When the gravitational wave stretches the arms, it imparts a tiny oscillating phase shift onto the laser light.
Yeah.
In wave physics, when you phase modulate a carrier wave, you create what are called sidebands.
Let's break that down. Sidebands?
Imagine the main 1064 nanometer laser light is the carrier frequency.
Right.
When the gravitational wave oscillates the mirror at, say, 100 hertz, it creates new frequencies of light, one slightly above the carrier frequency and one slightly below.
Okay, I'm following.
These are the audio frequency sidebands, and they're the only part of the light that actually contains the signal of the gravitational wave.
Okay, so the main carrier light is basically blind to the gravitational wave, but it generates these tiny sideband frequencies that carry the actual fingerprint of the collision.
Exactly. Now, what's fascinating here is how the signal recycling mirror gives the engineers a tuning knob for these sidebands.
Tuning knob.
Yeah, the signal recycling cavity decouples the storage time of the main carrier light in the arms from the storage time of the signal sidebands.
Meaning the main 750 kilowatts of laser light can stay trapped in the 4-kilometer arms for one amount of time, bouncing back and forth, but the actual signal, the sidebands, can be manipulated separately before they hit the detector.
Precisely. Advanced LIGO operates primarily in a regime called resonant sideband extraction, or RSE.
How does resonant sideband extraction work mechanically?
It's all about resonance. If the sidebands stay trapped in the 4-kilometer arms for too long, they can actually start to destructively interfere with themselves, especially for high-frequency gravitational waves.
Because the wave is oscillating so fast.
Exactly. The wave oscillates so fast that the mirror moves in and out while the sideband light is still trapped, which washes out the signal completely.
Oh, wow.
So the signal recycling mirror is placed at exactly the right microscopic distance to create a resonance condition that effectively extracts those sidebands out of the main arms faster than they would naturally leak out.
It's like tuning a radio antenna.
Yeah, exactly.
Instead of just throwing up a generic wire and hoping you catch all the static, you are adjusting the physical shape of your antenna so it specifically amplifies the exact frequency you want while letting the signal escape before it muddles itself.
That's a brilliant way to conceptualize it. By changing the microscopic position and the reflectivity of this signal recycling mirror, you can dynamically tune the interferometer's response.
That's incredible.
You broaden the bandwidth and restore sensitivity at high frequencies. This is vital because it allows the scientists to optimize the entire instrument's response, specifically to get the best signal-to-noise ratio for a compact binary and spiral.
Like the high-frequency chirp of two neutron stars in their final moments before merging?
Exactly.
So instead of just having a static one-size-fits-all net, you can mathematically tune the shape of your net based on what kind of cosmic fish you are trying to catch.
Right.
But tuning that high-frequency sensitivity brings us right to the edge of an incredibly frustrating physical limit, the struggle with light itself.
Yes. The battle against quantum mechanics.
Up until now, we've talked about lasers as if they are perfectly continuous streams of energy, like water flowing smoothly from a hose.
Right, which they aren't.
Exactly.
Yeah.
At this insane scale of precision, measuring 10 to the negative 18th meters, we have to deal with the fundamental reality that light is quantized. It is made of individual particles or packets of energy called photons. And this introduces two completely opposing types of quantum noise that dictate the entire engineering architecture of advanced LIGO. Let's start with the first one, which is shot noise.
Shot noise is a direct consequence of the quantum nature of light you just described. If you look closely enough at the laser beam hitting the photodetector, it is not a smooth, continuous wave.
Right.
It is governed by Poisson's statistics. The photons arrive at random, discrete intervals.
The source material describes it as a noisy parade of individual photons, where each one arrives with a little statistical pop.
I love that description. Because the arrival time is statistical, there is inherent uncertainty in exactly how much light is arriving at any given microsecond.
Okay.
This statistical uncertainty creates a literal crackle or a hiss in the data. Think of rain falling on a tin roof.
Oh, that makes sense.
A few drops make discrete, loud pings. A downpour sounds like a continuous roar, but there are still fluctuations in the intensity of the sound. This crackle dominates the detector's sensitivity at high frequencies, mostly anything above 100 Hz.
Right. If you're looking for a tiny flicker in the light caused by a gravitational wave, but the light itself is statistically flickering just because photons are random, you can't see the signal.
Exactly.
And the standard way to beat statistical uncertainty is to increase the sample size.
Yes, if you have more photons, the average arrival rate smooths out.
Right.
Mathematically, the shot noise decreases as the inverse square root of the number of photons, or the laser power. This is exactly why advanced LIGO needs that massive 750 kilowatts of circulating power.
More power equals more photons.
Which smooths out the statistical arrival time and lowers the high-frequency shot noise.
Okay, so logically the problem is solved. Just turn up the power, flood the 4-kilometer arms with as many photons as possible, smooth out the noisy parade, and catch the high-frequency waves.
If only it were that simple.
Right, because this is where the universe gives us a massive, almost cruel catch-22 because of the second phase of quantum noise, which is radiation pressure noise.
Yes. This is where the sheer physics of light becomes a mechanical problem. Photons may not have mass, but according to quantum mechanics and relativity, they do have momentum.
Okay.
When a photon reflects off a mirror, it transfers twice its momentum to that mirror. When 750 kilowatts of laser light hits a suspended glass mirror, it exerts a massive physical pushing force.
And because we just established that the arrival of those photons is statistically fluctuating, that crackling, noisy parade, the physical pushing force on the mirrors is also fluctuating?
Precisely. You are dealing with time-varying radiation pressure. It physically kicks the mirrors around.
Wow.
And unlike shot noise, which gets better with more power, the mechanical displacement caused by radiation pressure noise scales proportionally with the square root of the circulating laser power.
Oh, no.
Yeah, and it is dominant at low frequencies, mostly below 50 hertz.
So, to reiterate, if you turn up the laser power to fix your high-frequency shot noise, the sheer physical momentum of all those extra photons kicks the suspended mirrors around and completely masks your low-frequency gravitational wave signals.
Yep.
You fix one end of the spectrum by totally destroying the other.
It is the macroscopic manifestation of the Heisenberg uncertainty principle, written across a 4-kilometer machine.
That is wild.
It's the standard quantum limit. You cannot simultaneously know both the phase of the light field, which relates to shot noise, and the amplitude of the light field, which relates to radiation pressure, with perfect precision.
So how do you fight the Heisenberg uncertainty principle? The first solution the engineers deployed is wonderfully straightforward and entirely brute force.
Right.
If the light is kicking the mirrors too hard, well, just make the mirrors heavier.
That is exactly the first line of defense. The physical displacement caused by quantum radiation pressure noise scales inversely with the mass of the mirror and the square of the frequency. The mathematical relationship is 1 over mf squared.
Oh.
So to resist that fluctuating photon pressure, advanced LIGO upgraded the test masses from their initial weights to a massive 40 kilograms each.
40 kilograms. That's almost 90 pounds of solid, perfectly pure glass suspended in a vacuum just to resist the physical push of a beam of light.
It's incredible, and it helps significantly mitigate the kick at those crucial low frequencies.
Right.
But to truly bypass this power-dependent trade-off, simply adding mass wasn't enough. They needed a profoundly elegant quantum mechanical solution.
And what was that?
They found it by injecting something called frequency-dependent squeezed vacuum states into the detector.
Okay, I read this section of the physics paper 3 times. Squeezed vacuum states. What is actually happening here, physically?
To grasp this, we have to realize that even in a total vacuum, even inside the ultra-high vacuum tubes of LIGO when no laser light is present, empty space is not truly empty.
Wait.
Quantum field theory dictates that the vacuum is boiling with zero-point energy. Tiny electromagnetic fluctuations are constantly popping into and out of existence.
So empty space has a baseline level of quantum static.
Yes. And these random vacuum fluctuations actually enter the interferometer from the outside world, specifically at the dark port, the output where the detector sits.
Okay.
These vacuum fluctuations travel backward into the machine, mix with the laser light at the beam splitter, and beat against the carrier light. That interaction is actually what causes both the shot noise and the radiation pressure noise.
Wait, really? The empty space outside the machine is leaking in and contaminating the perfectly stabilized laser?
Essentially, yes. The vacuum state is the source of the uncertainty.
That is mind-blowing.
So the advanced LIGO team decided that if they couldn't stop the vacuum from entering, they would modify the vacuum before it got in.
How do you modify a vacuum?
They use a device called an in-vacuum nonlinear optical parametric oscillator, or OPO.
An optical parametric oscillator. Let's break down how that modifies empty space.
Inside the OPO, there is a nonlinear crystal, typically periodically poled potassium titanal phosphate.
Okay.
They pump this crystal with a green laser. Because of the crystal's nonlinear optical properties, a high-energy green photon will spontaneously split into 2 lower-energy infrared photons.
And why does that matter?
Because these 2 new photons are quantum mechanically entangled. They're perfectly correlated. By interacting the vacuum state with this crystal, the OPO takes those random spherical vacuum fluctuations and squeezes them.
This is where my absolute favorite analogy from the notes comes in.
Oh, the water balloon.
Yes. Imagine the fundamental quantum uncertainty of the vacuum is a water balloon. Heisenberg's uncertainty principle is a strict law that says you cannot change the total volume of water in that balloon.
Right. The total amount of uncertainty is absolutely fixed by the universe.
But you can squeeze the balloon. If you squeeze it with your hands in the middle, it gets really thin in one direction, but it bulges out massively in the other.
That is an exceptionally helpful way to visualize quantum phase space. You are taking the fundamental uncertainty and redistributing it.
Right.
You reduce the noise in one property, say, the phase quadrature, making the balloon thin there at the expense of increasing the noise of the other property, the amplitude quadrature, where the balloon bulges.
But because we have that catch-22 with high and low frequencies, we need the balloon squeezed differently at different times.
Exactly.
At high frequencies, above 100 hertz, shot noise is killing us, so we want the balloon thin in the phase direction. But at low frequencies, below 50 hertz, radiation pressure is kicking the mirrors, so we need the balloon thin in the amplitude direction.
Exactly. You need the squeezing to rotate depending on the frequency, and that is why it must be frequency-dependent squeezing.
Okay, so how do they rotate it?
To achieve this, after they generate the squeezed vacuum state in the OPO, they reflect it off a detuned 10-meter scale Fabry-Perot resonator known as a filter cavity.
They built a 10-meter vacuum tube mirror cavity just to bounce empty space around.
Yes, because this filter cavity introduces a frequency-dependent phase shift. It acts like a dispersive prism for the quantum vacuum.
Oh, wow.
As this modified vacuum state reflects out of the filter cavity and enters the interferometer's dark port, it is phase squeezed at high frequencies to suppress the shot noise.
Right.
But as you move down the frequency spectrum, the filter cavity seamlessly rotates the squeezing ellipse so that it becomes amplitude squeezed at low frequencies, suppressing the radiation pressure noise.
It's like performing judo on the laws of physics.
It really is.
You can't beat Heisenberg's uncertainty principle, so you use a 10-meter mirror cavity to twist the uncertainty so it constantly hides in the blind spots of your detector. You perfectly dodge the noise at both ends of the spectrum simultaneously.
It is arguably one of the most sophisticated applications of quantum mechanics in modern engineering. It ameliorates quantum noise across the entire broadband spectrum, allowing them to surpass the standard quantum limit.
Which brings us to the physical objects that actually have to handle all this quantum trickery and 750 kilowatts of power. The super mirrors.
Yes. The mirrors.
Because if you have that much power bouncing back and forth, those mirrors have to be fundamentally perfect. You can't just order a telescope mirror from a catalog.
Not even close.
Yeah.
The physical specifications of these test masses are almost incomprehensible. As we mentioned, they are fused silica cylinders weighing 40 kilograms.
Right.
They are massive, 34 centimeters in diameter and 20 centimeters thick.
So it's a cylinder about the size of a very thick, large pizza, but made of 90 pounds of incredibly dense, perfectly transparent glass.
Right, and the surface of these mirrors is what they call super polished.
How polished is super polished?
The documentation states they are polished to a precision of lambda over 800 across the central 10 centimeters of the face.
Let's translate that. Lambda means the wavelengths of the laser light, which we established is 164 nanometers.
Correct. So if you divide 1064 nanometers by 800, you get a surface roughness of about 1 nanometer root mean square.
1 nanometer. To put that in perspective, if you scaled that 34 centimeter mirror up to the size of the Earth, the tallest mountain or deepest valley on its surface would be a fraction of an inch high.
That's a great visualization.
It is functionally as flat as a physical object can be without violating atomic physics.
And achieving that requires techniques like ion beam figuring, where they literally blast individual atoms off the surface to smooth it out.
That's crazy.
But the shape is just the substrate. The real magic and the real challenge is the coating.
Right.
The input mirrors are designed to allow a tiny bit of light into the cavity, so they have a precisely tuned 1.4% transmission rate.
Okay.
But the end mirrors, the ones at the far end of the 4-kilometer arms, are high reflectors. They have a transmission of just 5 parts per million.
5 parts per million, meaning 99.99995% of the 750 kilowatts of light bounces perfectly back. How do you make glass that reflective? Standard silvering on the back of a bathroom mirror absorbs way too much light.
You have to use dielectric coatings. It's a highly uniform, multi-layer coating consisting of alternating quarter-wave doublets of silica, which is SiO2, and tantalum pentoxide, or Te2O5, commonly called Tantala.
Let's unpack the physics of why alternating layers work. Why not just one thick layer of something shiny?
It relies on the principle of a Bragg reflector. Silica and tantala have different refractive indices, meaning light travels at slightly different speeds through them.
Right.
When light hits the boundary between a high-index material and a low-index material, a portion of it reflects. By making each layer exactly 1/4 the thickness of the laser's wavelength, the reflections from every single boundary interface perfectly constructively interfere with each other.
So it's microscopic layers of different glass and metal oxides stacked like a molecular crepe cake.
Yes.
Each layer reflects a tiny bit of light, but because they're spaced at exactly a 1/4 wavelength apart, all those tiny reflections add up into one massive, perfect bounce. But why go to this extreme, excruciating level of perfection?
It's primarily about noise mitigation and thermal management. At 750 kilowatts of circulating power, any imperfection is catastrophic.
Because of the heat?
Exactly. The two enemies here are scatter and absorption. If even 1 part per million of the laser light is absorbed by the mirror coating, that absorbed optical energy turns into heat.
And heat causes things to expand.
Exactly. Even fused silica expands slightly when heated. This causes a thermal distortion in the center of the mirror, creating a physical bulge.
Oh, wow.
This alters the refractive index and changes the effective radius of curvature of the mirror. It acts like a thermal lens, which ruins the perfect Gaussian shape of the laser beam and degrades the resonant buildup.
So the beam gets messy again.
Right. They actually had to install active thermal compensation systems, basically ring heaters and auxiliary lasers, just to counteract this tiny bulging.
That makes total sense. And what about scatter? What happens if the light isn't absorbed but just bounces off at a weird angle because of a microscopic speck of dust?
If you scatter even a few parts per million of light out of the main beam, it shoots off into the vacuum tube. It can hit the steel walls of the tube, pick up the seismic vibrations of the steel, and then bounce back into the main beam.
Oh, wow. So suddenly your perfectly isolated laser beam is contaminated with the vibration of a steel pipe blowing in the wind instead of a black hole collision.
Precisely. Both thermal lensing and scattered light lead to wavefront distortions. If the wavefronts from the two 4-kilometer arms don't match perfectly when they return to the beam splitter, they can't perfectly destructively interfere.
Right. The dark fringe wouldn't be completely dark.
Exactly. You get a contrast defect at the dark port. Light leaks out when it shouldn't, completely masking the gravitational wave signal. This is why the coatings must have optical losses of less than 1 part per million.
And why they lined the inside of the 4-kilometer vacuum tubes with incredibly sophisticated blackened baffles to catch and absorb any scattered photons before they can return.
Exactly. It's just layer upon layer of protection.
It's just a compounding cascade of perfection. Every solution requires a new level of engineering madness. Which brings us to the environmental problem.
Oh, the seismic noise.
Right. We just talked about measuring displacements of 10 to the negative 18th meters. We talked about mirrors polished to within a single nanometer. But the Earth itself is constantly shaking.
It never stops.
There are earthquakes, ocean waves crashing on the shores thousands of miles away, trucks driving on the highway, loggers cutting down trees near the Livingston site.
Even the wind pushing against the sides of nearby buildings creates microseismic noise that travels through the ground.
Yeah.
The Earth is just a noisy, vibrating drum.
Right. And advanced LEGO wanted to push their low-frequency observation target down to 10 Hz, which is a massive improvement from initial LEGO's 40 Hz cutoffs.
Yeah.
To do that, they couldn't just filter the noise out of the data, they had to physically isolate these 40-kilogram super mirrors from the Earth entirely.
They needed to essentially stop the Earth from the mirror's perspective. The solution was an active and passive isolation upgrade heavily based on the GEO 600 detector, which was pioneered by teams in Germany and the UK.
Okay, what was the setup?
They moved from a single-stage suspension system to a quadruple pendulum.
Let's break down the mechanics of a quadruple pendulum. We're talking about 4 pendulums stacked sequentially on top of each other.
Yes. The main chain consists of 4 massive stages, hanging one from the other. The key here is how pendulums act as mechanical low-pass filters.
Okay.
Above its resonant frequency, a pendulum isolates the suspended mass from vibrations at the top point. For a single pendulum, the transmission of high-frequency vibration falls off as 1 over the frequency squared.
So if a high-frequency vibration from the ground hits the top of the pendulum, it gets significantly reduced by the time it reaches the bottom.
Exactly. Now stack 4 of them. By doing so, the system acts as an 8th-order low-pass filter. The vibration reduction multiplies. The tiny bit of vibration that makes it through the first stage hits the second pendulum and gets reduced even more. By the time you get to the 4th stage, The 40-kilogram test mass, the high-frequency seismic noise from the Earth, is practically suppressed to zero.
It's mechanical isolation through sequential attenuation.
Ah.
But they didn't just use strings.
No, they incorporated 3 stages of merging steel blade springs for enhanced vertical isolation.
Vertical isolation.
This is critical because the curvature of the Earth over 4 kilometers means that vertical shaking at the stations actually cross-couples into horizontal motion along the laser beam path. So you have to isolate vertically just as well as horizontally.
Okay, so you've built this massive multi-stage shock absorber, and the high-frequency seismic noise from the ground is gone. But there's another much more insidious source of vibration that comes from the materials themselves, right? Internal thermal noise.
Yes. This is governed by the fluctuation dissipation theorem. Everything has a temperature above absolute zero, which means the atoms inside all materials are constantly jiggling around. This is Brownian motion.
So even if you perfectly isolate the mirror from the ground shaking, the atoms inside the mirror and the wires holding it are vibrating just from the ambient temperature of being in a room.
Yes. In initial LIGO, the mirrors were suspended by steel music wire in a sling. But steel has high internal friction. When it bends, energy dissipates as heat.
Right.
This mechanical dissipation couples directly to thermal noise in the observation band. The steel wires were essentially humming with thermal energy right in the most sensitive frequency band, around 10 to 100 hertz.
So you can't use steel for the final stage holding the mirror. What did they replace it with in advanced LIGO?
They shifted to a monolithic fused silica suspension.
Meaning?
The final 40-kilogram silica test mass is suspended from the mass right above it, the penultimate mass, which is also a 40-kilogram block of silica. And they are connected by 4 ultra-high Q fused silica fibers.
So, glass threads. They hung a 90-pound glass mirror from another glass block using thin glass threads.
Exactly. Fused silica has an exceptionally high mechanical quality factor, or Q.
Let's explain Q factor. I like to think of it like striking a tuning fork versus hitting a piece of wood.
Perfect analogy.
If you hit wood, it makes a dull thud. The energy dissipates instantly across a broad range of frequencies. That's low Q.
Right. But if you strike a tuning fork, it wings with a pure tone for a very long time. That's high Q. The energy is highly concentrated at one specific resonant frequency.
Okay.
By making the entire final stage out of fused silica, they concentrate all that unavoidable thermal Brownian motion into very narrow frequency bands, the resonant modes of the fibers, leaving the rest of the broadband spectrum astonishingly quiet.
But to achieve that perfect ring, they couldn't just tie a knot with the glass fibers, right? Any mechanical clamp or knot would introduce friction, rubbing, and lower the Q factor.
Correct. To eliminate all rubbing friction, the assembly process had to be entirely monolithic. The silica fibers are actually welded directly to what they call silica ears.
Ears?
Yeah, these ears are small glass blocks attached to the flat sides of the 40-kilogram masses.
Yeah.
But how they attach those ears is a marvel of chemistry. They use a technique called hydroxide catalysis bonding, commonly known as silicate bonding.
I read about the silicate bonding process, and it totally fascinated me. Because it's not glue, right? Glue would introduce mechanical loss.
No, it's not an adhesive. It's a chemical process originally developed for the Gravity Probe B satellite.
How does it work?
A hydroxide solution, essentially a tiny bit of water with a high pH, is placed between the incredibly flat surfaces of the silica ear and the massive silica mirror.
And that hydroxide actually chemically attacks the glass, doesn't it?
Yes. It temporarily dissolves the surface layer of the silica, breaking the siloxane bonds. As the solution cures and the water evaporates over weeks, a new silicate network forms across the microscopic gap. The two pieces of glass repolymerize. They literally bond at the molecular level.
So the top glass mass, the 4 glass fibers, and the bottom 40-kilogram glass mirror, functionally they aren't separate parts anymore.
Right.
They're a single, continuous, monolithic, crystalline structure of glass. It's chemical healing.
Exactly. This monolithic structure is what pushes the thermal displacement noise down to that unfathomable 10 to the negative 19th meters per root hertz target.
But wait, I have to inject some practical reality here.
Okay.
You have a 90-pound chunk of glass hanging from thin glass fibers chemically bonded together. If an earthquake hits Louisiana, or if a vacuum pump suddenly fails and causes a shock wave, Doesn't the whole thing just shatter?
It's a very real concern.
I mean, if it's a giant, delicate glass pendulum, what happens when it swings too far?
The engineers absolutely had to account for catastrophic failure. The suspension cages feature specific earthquake stops, basically bumpers that sit just millimeters away from the glass mass to catch it if it swings too wildly.
But you can't use standard metal bumpers, right? Because metal hitting glass is a recipe for a crack.
Not only could metal scratch the silica, but more importantly, metal interacting with a dielectric like glass causes triboelectric charging.
Okay, what is that?
It builds up a static electric charge.
Ah, because glass loves static electricity.
Yeah.
Like rubbing a balloon on your hair.
Right. And if the mirror builds up a static charge, it will interact with the metal cage around it, creating excess electrical noise that masks the gravitational waves.
Oh, that would be bad.
So for the final silica masses, they designed highly specific earthquake stops made of a fluoroelastomer, a durable synthetic rubber fitted with specific silica inserts.
Smart.
This safely catches the mass in an emergency without transferring static charge or mechanically shocking the monolithic structure.
The attention to detail is just staggering. Every single problem spawns 3 more problems that require entirely new fields of material science to solve.
It really does.
But this perfectly isolates the mirror, which raises a massive paradox. And this is the crux of the control engineering challenge.
Yes, the control paradox.
You have just spent millions of dollars, complex seismic isolation platforms, quadruple pendulums, and chemically welded glass fibers to perfectly isolate this 40-kilogram mirror from the entire universe.
Yep.
It is hanging there, utterly pristine, perfectly still, but you still have to actively control it. As we established earlier, the interferometer has to be actively held on a dark fringe, meaning the arm lengths have to be adjusted continuously so the laser light destructively interferes perfectly at the output port, just waiting for a gravitational wave to pass.
Right.
So how do you push a mirror that you have perfectly isolated from touching anything?
Is the ultimate engineering paradox. If you push it mechanically with a motor or a rod, you instantly reintroduce all the seismic and mechanical noise you just spent years trying to filter out.
Right, you short-circuit your own isolation.
Exactly. The solution they came up with is brilliant. Right behind the main quadruple suspension chain, hanging just millimeters away, is a second quadruple pendulum called the reaction chain.
Wait, they built an entire shadow pendulum just to sit behind the main one?
Essentially, yes. It sits on the exact same quiet, seismically isolated platform at the top. Because it is also a quadruple pendulum, its bottom mass, the end reaction mass, or ERM, is just as isolated from the Earth as the main test mass itself.
Okay.
And from this perfectly quiet floating reference point, they apply global control signals across a tiny millimeter-scale gap.
How do they bridge the gap without touching it?
They use an electrostatic drive, or ESD.
An electrostatic drive? Are you saying they push the 40-kilogram main mirror around using static electricity?
That is exactly what they do. They deposit a pattern of gold traces, interlocking comb-like electrodes onto the face of the reaction mass.
Wow.
They apply precise voltages to these gold traces, which generates a fringing electric field. Because the main test mass is made of fused silica, which is a dielectric material, the electric field gently polarizes the glass and pulls on it.
It's like engineering telekinesis. You are holding a perfectly quiet piece of glass, and you are using an electric field from a shadow piece of glass to pull it back and forth by a few nanometers to keep the laser tuned.
It allows them to apply actuation forces with zero mechanical contact, entirely preserving the thermal and seismic isolation.
That is genius.
But that's only at the very bottom stage. They also need local control at the higher stages of the quadruple pendulum to damp out low-frequency swinging, like the whole pendulum swaying back and forth at 1 or 2 hertz.
Right, you have to stop the big swings.
For this, they use sensors and actuators called bosoms.
Let's unpack bosoms. How do they work?
A bosom is an integrated shadow sensor and electromagnetic actuator. They are arranged around the upper masses of the suspension chains. The sensor part uses an infrared LED projecting a beam of light across a small gap to a photodiode. Attached to the suspended mass is a tiny fin, or flag, that sits right in that gap.
So as the pendulum swings, the fin moves in and out of the light beam, blocking more or less of the infrared light, allowing the photodiode to perfectly measure the swinging motion.
Exactly. Once the sensor measures the swing, the actuator kicks in. The actuator is a coil magnet system, similar to how a speaker cone works.
Oh, okay.
A tiny permanent magnet is attached to the mass, and a coil of wire is fixed to the rigid cage. By running a current through the coil, they create a magnetic field that pushes or pulls on the magnet, applying a correction force to stabilize the pendulum.
So they use light shadows and magnetic coils at the top stages to steady the bulk swinging, and incredibly fine static electricity at the bottom to hold the main mirror perfectly in place for the laser.
Exactly.
It sounds flawless on paper, but I read in the sources that getting this dynamic control system to work wasn't exactly smooth sailing. There were real-world engineering hurdles that completely baffled the team.
Unsurprisingly, yes. When you are pushing the boundaries of material physics, the materials often push back.
Right.
During the prototyping phase at LASTS, the LIGO Advanced Systems Test Interferometer Facility at MIT, they encountered a bizarre, frustrating issue that they dubbed the anomalous tilt.
What exactly was the anomalous tilt?
They were testing the upper stages of the quadruple pendulum. They discovered that if a mass in the upper chain was tilted, say, they deliberately pitched it forward during an alignment test, and then they slowly, carefully released the control force, the mass wouldn't return to its original plumb starting position.
Wait, gravity didn't pull it straight down. It was like the pendulum had a memory of being bent.
Exactly. To give you the numbers from the report, if they applied a 25 milliradian tilt to the upper intermediate mass and gently released it, it would leave a 1.5 milliradian static offset in the suspension.
The mass just stayed crooked.
Yeah. The only way to clear this memory was to pull the mass far away and let it snap back rapidly and oscillate wildly until it finally settled.
That is a nightmare for an instrument that requires sub-nanometer alignment. What on earth was causing a pendulum to just decide to hang crookedly?
After extensive exploration and ruling out rubbing or sensor errors, they traced the root cause back to hysteresis in the metal suspension wires of the upper stages.
Let's break down hysteresis in this context.
The upper stages use marriaging steel wires. When you bend a metal wire, the internal crystalline lattice of the metal undergoes microscopic deformations.
Okay.
In a perfect world, when you let go, it springs back perfectly. But real metals exhibit hysteresis, a lagging effect where the internal structure retains a tiny amount of stress or deformation. The metal was basically creeping and holding the bend.
So how do they fix it? You can't just have your mirror permanently tilted every time a large, low-frequency rumble comes through the earth and sways the pendulum.
They couldn't change the material without ruining the vertical isolation, so they had to change the physics of the suspension geometry itself. The fix required moving the break-off points of the suspension wires.
The break-off point being the exact spot where the wire leaves the clamp and supports the mass.
Right. By physically raising the distance between those break-off points and the center of mass of the block, they significantly increased the gravitational restoring torque.
So they tweaked the center of gravity, essentially giving gravity a longer lever arm to pull the mass harder back to true zero, physically overpowering the internal memory of the metal.
Exactly. They used gravity to beat the hysteresis. But on top of that physical fix, they also had to implement highly sophisticated digital control algorithms.
Because of the sensor noise.
Yes. Remember, those boson sensors at the top have their own electronic noise. If you use a simple aggressive feedback loop to hold the pendulum still, you end up injecting the sensor noise right into the mirror, completely ruining the sensitive 10 Hz band.
So how do you push it without pushing the noise into it?
They moved away from simple local damping and implemented modern state-space control theory techniques, specifically something called modal damping for the critical x-axis, which is the axis along the main laser beam.
Modal damping. Let's translate that. This means they aren't just pushing blindly against a swing, right?
Correct. A quadruple pendulum is a complex coupled oscillator.
Yeah.
It doesn't just swing back and forth like a grandfather clock.
Right, it's 4 pieces.
It has multiple mathematical eigenmodes, distinct patterns of motion where the 4 masses interact. Sometimes they swing together, sometimes they swing in opposite directions.
Okay.
Modal damping uses the sensors to calculate exactly which eigenmode is currently resonating, and then applies a calculated combination of forces to all the actuators to damp that specific mode simultaneously.
It's like pushing someone on a swing. If you push at random times, you cause chaotic, jerky motion.
Exactly.
But if you watch the swing, calculate its exact period, and push at the exact right moment at the peak of the arc, you smoothly change its momentum. Modal damping is observing the complex math of the pendulum and gracefully damping it without fighting it.
Precisely. It optimizes the balance between the strength of the damping and the residual technical noise that reaches the final test mass.
Yeah.
It's a delicate, continuous mathematical dance.
Wow.
You sense just enough to keep the mirror perfectly aligned for the dark fringe, but you filter and shape the feedback so flawlessly that you don't accidentally mimic the tiny push of a gravitational wave.
Which brings us to the end of our deep dive today. Let's just zoom out for a second and recap the sheer monumental scale of the technological triumph that is advanced LEGO.
It's a lot to take in.
We are talking about a machine that folds a 1,200-kilometer optical path into 4-kilometer tubes. It circulates 750 kilowatts of ultra-pure infrared laser power, which is enough energy to instantly melt steel, but perfectly bounces it off 40-kilogram super-polished glass masses that are so mathematically flat that a mountain on them would be less than an inch high.
Right.
To beat the fundamental limits of quantum mechanics, they literally squeeze the vacuum of empty space using a 10-meter dispersive cavity to twist the quantum uncertainty to suppress the statistical crackle of photons and the physical kick of radiation pressure.
It's incredible.
And they isolate this entire chaotic, violent energy by hanging it from monolithic, chemically welded glass threads on a quadruple pendulum, controlling it all across a microscopic gap using static electricity and modal eigenode damping. All of this, every single ounce of this effort, is just to measure a change in distance of 1/1000th the width of a proton.
It is arguably the most sensitive, most perfectly engineered instrument ever constructed by humanity.
Truly.
But if we connect all of this staggering physical engineering to the bigger picture, the theoretical physics that necessitated it, there is a profound, almost poetic symmetry that emerges from the source documentation.
I saw that at the very end of the physics papers. How so?
Well, in the theoretical documentation we reviewed detailing how scientists actually calculate the waveforms they are looking for, there is a complex section on the effect of one-body, or EOB, Hamiltonian, and post-Minkowskian scattering.
Right, because when theoretical physicists try to calculate the gravitational waves emitted by two massive black holes colliding, the math is incomprehensibly complex.
Oh, absolutely.
Einstein's equations of general relativity get incredibly messy and nonlinear when two black holes are in a chaotic, spiraling two-body death dance in extreme, highly curved space-time.
Exactly. It's a mathematical nightmare.
Huh?
So, to actually solve it, brilliant theorists like Alessandro Bonanno and Hebo de Moore utilized a mathematical trick called a canonical transformation.
Let's break down a canonical transformation for a second. In simple terms, that's like taking a math problem that has way too many chaotic moving parts and shifting your mathematical perspective, changing your coordinate system so it looks like a much simpler problem without changing the fundamental physics, right?
That is exactly right. The EOB Hamiltonian mathematically maps those two chaotic, swirling, colliding black holes into a single, elegant, effective one-body test mass moving quietly in a deformed background spacetime.
Okay.
They mathematically reduce the extreme chaos of the binary universe down to the predictable dynamics of one single, perfectly understood test mass.
Wait, that's exactly what the engineers did.
Yes. Isn't it beautiful? Advanced LEGO's engineers did the exact same thing in physical reality, just in reverse.
Wow.
They took a chaotic, vibrating, noisy universe filled with quantum vacuum fluctuations, crashing ocean waves, rumbling trucks, and thermal Brownian motion, and they painstakingly engineered it all away.
Yeah.
They isolated and filtered and damped the world down to one single, perfectly still 40-kilogram test mass.
They built the physical, macroscopic manifestation of the theoretical physics equations. The traditional mega-engineering blueprints didn't work. Brute force doesn't let you listen to the universe.
No, it doesn't.
You don't fight the hurricane by building a thicker wall and anchoring it to the bedrock. You fight it by suspending a perfect piece of glass on a glass thread, isolating it from absolutely everything else, and letting the whisper of space-time itself be the only thing in the universe that can move it.
The symmetry between the theoretical abstraction of the cosmos and the physical reality of the detector is absolute perfection.
Something profound to ponder the next time you look up at the night sky and wonder what invisible waves are passing right through you. Until next time, keep exploring.
So imagine trying to measure the distance from our solar system all the way to Alpha Centauri, which is, over 4 light years away, and demanding a margin of error that's no thicker than a single human hair.
Right, it completely breaks your brain because at that scale, which is 10 to the negative 19 meters, normal rulers are totally useless.
Yeah.
I mean, you are in a regime where the physics of the tools themselves actually fight against you. Our standard intuitions about solid matter and empty space they completely fall apart.
Which brings us perfectly to the mission of today's deep dive. Welcome, everyone. Today we are unpacking the specific, honestly mind-bending technological architecture that transformed the initial LEGO observatory into advanced LEGO.
It's quite the upgrade.
It really is. We've got this massive stack of sources for you today. Engineering schematics, optical layout papers, quantum noise phenomenology, and we're just extracting the core mechanisms that allow this machine to measure a change in distance on the order of like 10,000th the width of a proton.
And, understanding this architecture means understanding the specific physical noise floors it was designed to get around.
Right.
The signal of a gravitational wave is agonizingly weak. So the entire engineering philosophy of advanced LEGO is basically about aggressively lowering that noise floor across these distinct frequency bands.
And the staggering statistic here from the sources is that advanced LEGO was engineered to be roughly 10 times more sensitive than the initial run, which, when you first hear a factor of 10, it sounds like, I don't know, a nice incremental update.
Yeah, a solid improvement, right. But it's so much more than that. Because we operate in a three-dimensional universe, your observational volume scales as the cube of your sensitivity.
Oh, wow, so 10 cubed.
Exactly. By pushing that sensitivity limit out 10 times further in every direction, advanced LEGO expanded our observational volume of the universe by a factor of 1,000.
1,000. That's insane.
It is. You immediately transition from just monitoring a small local neighborhood of the cosmos to listening to a sphere packed with thousands of times more galaxies, which vastly increases the statistical probability of actually detecting binary black hole and neutron star in spirals.
Okay, but before you can listen to it in spiral a billion light years away, you have to physically decouple your instrument from the planet it's sitting on, right? I mean, Earth is just this chaotic, vibrating mass.
Oh, absolutely. It's terribly noisy.
You've got microseismic peaks from ocean waves crashing on continental shelves, tectonic shifts, and just local anthropogenic noise like literal highway traffic.
Yeah, trucks driving by. This is the domain of low-frequency noise. Now, initial LEGO relied heavily on passive seismic isolation, so basically stacks of metal and springs.
Kind of like heavy car suspension.
Sort of, yeah. It absorbs energy, but fundamentally a passive system still provides a physical, mechanical path for low-frequency ground motion to just travel right up into the instrument.
I gotcha.
So advanced LEGO required a transition to a fully active feed-forward and feedback internal seismic isolation system, or the ISI.
Okay, so how does the ISI actively cancel that motion? Because when I hear that, I picture a pair of noise-canceling headphones, using a microphone to sample ambient sound and a speaker to play an inverted waveform. But doing that with a multi-ton vacuum chamber sounds, well, it implies some intense mechanical actuation.
It's exactly that principle, actually, just on a massive, heavy scale. The mechanism relies on an array of highly sensitive inertial sensors, mostly geophones and seismometers, combined with relative position sensors.
Okay.
But the challenge is that no single sensor is perfectly accurate across all the frequencies they care about. So the control system uses these things called blending filters.
Blending filters.
Yeah, it takes the low-frequency data from the position sensors and then the high-frequency data from the geophones, digitally blends them to synthesize this perfect picture of the platform's motion, and then, this is the crazy part, feeds that signal into a network of hydraulic and electromagnetic actuators.
Wait, so the computer calculates the exact inverse trajectory of the Earth's vibration and physically drives the platform in the opposite direction in real time?
Yes, they are dynamically, physically fighting the Earth.
That is wild.
And the feed-forward aspect is crucial. By placing seismometers outside the facility, they can actually detect incoming seismic waves before they even reach the building.
So they see the wave coming.
Exactly, which allows the actuators to prepare the counter motion proactively.
Unbelievable. But that active isolation platform, that's just the first tier, right? Because once you move inside the vacuum envelope to the actual optic suspensions themselves, the sources say advanced LEGO uses a quadruple pendulum design, just cascading 4 masses in sequence.
Right. Because the physics of a pendulum naturally act as a mechanical low-pass filter.
Okay, break that down for me.
Well, above its resonant frequency, a single pendulum's ability to isolate against horizontal vibration scales as 1 over the frequency squared. So by hanging 4 pendulums in a chain, you multiply those isolation factors together. The quadruple pendulum operates as an 8th-order low-pass filter.
So the attenuation of the vibration just compounds drastically with every single stage.
Massively.
But wait, a standard string pendulum only isolates horizontally, right? It swings side to side. But the Earth is also vibrating up and down, vertically.
Which is exactly why the quadruple pendulum incorporates miraging steel blade springs at each of the upper stages.
Miraging steel.
Yeah, it's a specific type of steel that undergoes this highly controlled aging process to achieve immense yield strength, but without losing its malleability. It's ideal for vertical isolation.
I see.
So the combination of the active ISI and this cascaded suspension system means that by the time you reach the bottom mass, which is the mirror itself, the vibrations from the outside world have been attenuated by a factor of millions.
Millions. So this mechanical decoupling drops the lower end of LIGO's sensitivity band from, what, 40 hertz down to 10 hertz?
Yep, down to 10 hertz.
Which completely opens up the low-frequency universe.
Yeah.
I mean, giving astronomers a vastly earlier warning time for binary neutron star mergers.
Yeah.
Because they sweep up through those lower frequencies first.
Exactly. You've effectively silenced the environment, but once the external seismic noise is decoupled, you are confronted with the internal thermodynamics of the instrument itself.
Right, the mid-frequency band, which is dominated by thermal noise.
Yeah.
Because these 40-kilogram test masses, the main mirrors, they're made of ultra-pure fused silica. But they're at room temperature. And at room temp, the atoms inside that silica and the materials holding it are just constantly vibrating.
They're jiggling.
Jiggling, yeah. And if you're trying to measure a displacement of 10 to the negative 19 meters, the natural thermal jiggling of a room temperature mirror has to be completely overwhelming.
It is. I mean, temperature is essentially just atomic kinetic energy. And since we can't operate these massive optics at cryogenic temperatures because the continuous laser power would just heat them right back up, the total amount of thermal energy in the mirror is fixed.
Okay, so if you can't remove the heat, what do you do?
The engineering challenge is not removing the thermal noise, but forcing it into a frequency band where we aren't trying to measure gravitational waves.
And this comes down to the suspension fibers. The sources highlight that they hang this 40-kilogram fused silica optic using 4 fused silica fibers that are only like 0.4 millimeters thick.
Glass threads.
Literally threads of glass.
Yeah.
Holding up almost 90 pounds. Why on earth would you abandon high-tensile steel wire for glass threads? I mean, steel has massive load domain capacity and it doesn't shatter like glass.
It all comes down to a property called mechanical dissipation, which physicists parameterize as Q.
Okay, Q factor.
Right. Steel is highly dissipative. It has a low Q factor. Think about it. If you strike a steel block, the acoustic energy dissipates rapidly into heat, and it just produces this dull thud.
Yeah, like a clunk.
Exactly. That internal friction means that its thermal noise is broadly distributed, just smeared across the entire mid-frequency detection band. But fused silica, on the other hand, has an ultra-high Q factor.
Oh, so it rings like a perfectly pure bell, just sustaining a tone with almost zero internal friction.
Precisely. And there's this thing called the fluctuation dissipation theorem, which dictates that mechanical friction and thermal noise are intrinsically linked.
All right.
Because monolithic fused silica has incredibly low internal friction, the unavoidable thermal noise doesn't smear across the spectrum. Instead, it gets concentrated into intensely narrow frequency spikes right at the mechanical resonances of the fibers, which is around 500 hertz.
Oh, so you basically sweep all the thermal noise into a few localized peaks and leave the rest of the detection band, where the actual gravitational wave signals primarily exist, orders of magnitude quieter.
Exactly. You just push the noise out of the way.
That is incredibly elegant. But wait, practically speaking, how do you attach a delicate glass fiber to a massive glass mirror without using, like, mechanical clamps? Because wouldn't a metal clamp introduce friction and instantly ruin that beautiful high Q factor?
It would. It would ruin it completely. So they utilize this technique called hydroxide catalysis bonding, or silicate bonding.
Okay, how does that work?
You place a highly controlled, incredibly tiny volume of a potassium hydroxide solution between the flat surface of the fiber ear and the side of the optic. The solution chemically etches the silica surfaces, which frees up these siloxane chains.
All right.
And as the water evaporates from the solution, those chains cross-link.
Wait, so it's not just glue. You are chemically coaxing the two separate pieces of glass to literally share an atomic lattice.
Yes. It becomes a single, continuous, monolithic structure at the molecular level. There is no interface, there is no mechanical seam to introduce friction.
Yeah.
This monolithic fused silica suspension is what clears the mid-frequency band of thermal noise.
Okay, so the seismic noise floor is lowered. The thermal noise floor is lowered. The test mass is now eerily still. Now we actually have to measure its displacement using the laser interferometer.
The tricky part.
Right. Because to achieve the required sensitivity at high frequencies, the sources say advanced LIGO had to drastically increase their optical power.
They did, because high-frequency sensitivity is heavily constrained by quantum shot noise.
Shot noise, right. Because light consists of discrete photons.
Exactly. And because photon emission is a quantum Poisson process, they don't arrive at the photodetector in a perfectly smooth, continuous stream. They arrive with random statistical fluctuations.
So if the laser power is low, the arrival of photons is kind of erratic, like raindrops on a tin roof.
That's a great analogy, yeah. The variance in that arrival rate creates statistical uncertainty in the phase measurement of the laser. And the standard solution to that in physics is simply throw more photons at the problem, average out the statistical noise.
Okay, so just blast it with a stronger laser.
Exactly. Advanced LIGO boosted the input laser to roughly 200 watts. But to reduce the shot noise to the necessary levels, they needed far more power interacting with the actual test masses.
More than 200 watts.
Way more. They achieved this using a power recycling mirror, which they placed between the laser source and the beam splitter.
Ah, so this intentionally creates a resonant cavity before the light even enters the main arms.
Right. The power cycling mirror takes the light reflecting back toward the source and bounces it back into the interferometer, continually building up the amplitude of the carrier field.
Like pushing a swing at just the right time to make it go higher and higher.
Yes. And through this resonance, that 200-watt input is amplified to roughly 750 kilowatts of effective continuous wave power, just circulating inside the Fabry-Perot cavities in the arms.
750 kilowatts. You have almost a megawatt of optical power constantly reflecting off these 30-kilogram mirrors.
It's immense.
But wait, here is where my brain gets stuck. Light carries momentum, right?
It does.
So if you subject a perfectly suspended, perfectly still 40-kilogram optic to 750 kilowatts of continuous laser power, the sheer radiation pressure must exert a macroscopic physical force on the glass. It has to push it.
Oh, it definitely does. It pushes it hard. And because of the exact same photon arrival fluctuations that cause the shot noise in the first place, the radiation pressure pushing on the mirror is not perfectly constant. It fluctuates.
Oh, no.
Yeah. The laser is physically kicking the mirror randomly. This is called radiation pressure noise, and it totally corrupts the low-frequency sensitivity.
It's a trap. It's an inescapable quantum seesaw.
It really is.
To reduce the high-frequency shot noise, you increase the laser power. But that inevitably increases the low-frequency radiation pressure noise.
Yeah.
You are caught in a fundamental trap dictated by the Heisenberg uncertainty principle. By attempting to measure the position of the mirror with greater precision, you inevitably disturb its momentum.
Right. And this barrier is actually known as the standard quantum limit. For decades, physicists considered it a hard physical floor for interferometry. You just couldn't beat it. But the advanced iterations of LIGO utilize quantum engineering to literally shape the vacuum of space to bypass this limit.
Okay, shape the vacuum of space. That sounds like science fiction. But bypassing the uncertainty principle requires dealing with the dark port of the interferometer, right?
Yes.
Because the laser is tuned so that the light from the two arms destructively interferes at the output, which is the dark port, meaning no light reaches the detector unless a gravitational wave shifts the relative lengths of the arms. But from a quantum perspective, that dark port isn't actually empty.
Exactly. Because truly, empty space does not exist. The vacuum is boiling with virtual photons. Zero-point energy fluctuations just constantly popping in and out of existence. And these vacuum fluctuations enter the interferometer through the dark port, they propagate up the arms, they mix with the main laser field, and they are the actual fundamental source of both the shot noise and the radiation pressure noise.
So to fix the noise in the detector, you have to literally alter the quantum vacuum entering the dark port. And the sources describe this as injecting a squeezed vacuum state using an optical parametric oscillator, or OPO.
Right, the OPO. It contains a periodically poled nonlinear crystal.
Okay, what does that do?
Well, when you pump a high-energy laser through this specific type of crystal matrix, a process called spontaneous parametric down conversion occurs. A single high-energy photon is occasionally split into two lower-energy photons.
And because those two photons are born from the exact same parent particle at the exact same time, their quantum properties, their phase and amplitude, are heavily entangled.
Yes, and this entanglement is the key. It allows us to correlate the quantum fluctuations. In a standard, unmodified vacuum, the uncertainty in the phase and the uncertainty in the amplitude are perfectly equal. But by injecting these down-converted entangled photons into the dark port, we squeeze the uncertainty. We can drastically reduce the phase noise, which is the shot noise, at the direct expense of increasing the amplitude noise, the radiation pressure.
Okay, if we visualize the total quantum uncertainty as like a balloon filled with a fixed volume of air.
Great visual, yeah.
Squeezing the center of the balloon narrows it. That narrowing represents a drop in phase noise, giving you pristine high-frequency sensitivity. But the air is physically displaced to the ends of the balloon, causing them to bulge out.
Right.
And that bulge is the increased amplitude noise, meaning you've just made your low-frequency radiation pressure problem even worse.
Which is exactly where the A+ upgrade to advanced LIGO introduced frequency-dependent squeezing. Because just trading high-frequency sensitivity for low-frequency sensitivity isn't good enough anymore.
Right.
You need the vacuum to be squeezed in phase at high frequencies and squeezed in amplitude at low frequencies.
Meaning you need the balloon to physically rotate depending on the frequency of the gravitational wave you're trying to detect. But how do you rotate a quantum state?
It's brilliant. They installed an entirely new 300-meter-long vacuum tube adjacent to the main interferometer. They call it a filter cavity.
300 meters.
Yeah. Before the squeezed vacuum state even enters the dark port, it is reflected off this detuned cavity. The physics of the cavity are engineered so that high-frequency quantum fluctuations just reflect instantly, maintaining their phase-squeezed orientation.
Okay.
But low-frequency fluctuations actually enter the cavity, they resonate, and they acquire a specific phase shift before exiting.
Oh, so the time delay inside that specific cavity mathematically rotates the noise ellipse in quantum phase space.
Yes.
So by the time the vacuum state enters the interferometer, it has been sculpted perfectly. It delivers reduced shot noise at high frequencies and reduced radiation pressure noise at low frequencies. You are dynamically bypassing the standard quantum limit across the entire detection band.
It is honestly the ultimate manipulation of light and nothingness.
It's poetry.
And they pair this quantum sculpting with one final macroscopic optical upgrade, the signal recycling mirror, positioned right at the output port.
Wait, we have the power recycling mirror at the input to build up the main laser. Why place another mirror at the exit? Don't you want the gravitational wave signal to reach the photodetector, not bounce back into the machine?
You do, but when a gravitational wave stretches and compresses the arms, it modulates the laser light, generating what we call signal sidebands.
Okay.
These sidebands carry the actual astrophysical data, and the signal recycling mirror creates a resonant cavity specifically for these sidebands.
Oh, so the signal itself resonates and builds up inside the interferometer before finally passing through to the detector.
Exactly. And by physically moving the signal recycling mirror by just microscopic amounts, engineers can actually alter the phase of this resonance.
Meaning they can tune it?
Yeah. They can broaden the detector's bandwidth to look for the short, wideband frequency sweeps of binary mergers, or they can tune the resonance to an extremely narrow, highly sensitive peak to search for continuous gravitational waves, like the constant hum of an asymmetrical rotating pulsar.
So you aren't just building a passive receiver. You are actively reshaping the optical response of the machine to target specific astrophysics.
Exactly.
I mean, when you stack all of these systems together, the sheer complexity is just staggering. We're talking about an instrument that relies on digital blending filters, driving hydraulic actuators to instantly cancel oceanic microseisms.
Right.
It relies on massive fused silica monoliths, chemically bonded together to sequester thermal atomic vibrations into a 500 hertz corner.
Yep.
It uses a 750 kilowatt laser layout, capped with nonlinear crystals down-converting photons to rotate the quantum vacuum and literally cheat the Heisenberg uncertainty principle.
It's wild to hear it all listed out like that, but every single one of these distinct physics problems, seismic, thermal, optical, and quantum, had to be solved simultaneously just to measure a displacement of 10 to the negative 19 meters.
It sets a completely new benchmark for what precision engineering actually means in modern physics.
It really does. And, it forces us to look ahead.
How do you?
Well, if we are already building 300-meter vacuum cavities to mathematically rotate the quantum state of empty space just to hear the collision of local black holes,
Yeah.
We have to consider what happens when these isolation and squeezing techniques are pushed to their absolute theoretical limits in the coming decades.
Right.
When the noise floors are dropped so low that we bypass localized astrophysics entirely, we will eventually possess a gravitational wave detector so unimaginably sensitive that it picks up the stochastic background.
The stochastic background.
Yeah, the ambient chaotic gravitational waves left over from the inflationary epoch of the Big Bang itself.
So we'll literally be able to record the echoes of the birth of the universe.
We will.
Wow. To everyone listening, let that sink in for a bit,
Yeah.
because that is just profound. Thank you so much for joining us on this deep dive. Keep questioning the universe, keep wondering about the invisible forces around us, and we'll catch you on the next one.
To solve the most violent, massive classical physics problem in the universe, which is two black holes colliding, physicists had to steal a mathematical trick from the subatomic quantum world.
They really did. I mean, it is a remarkable story of theoretical survival, honestly.
Welcome to this deep dive. Today we are unpacking the effective one-body, or EOB, Hamiltonian formalism.
And this is really a framework that rescued classical general relativity from just a complete breakdown.
Right. It paved the very foundation that allows us to detect gravitational waves today. So if you are a physics graduate student staring down a thesis, or just an advanced learner who wants to get past the pop science analogies, this is for you.
We are getting into the real, unvarnished theoretical mechanics today.
Exactly. Our mission is to take you through the architecture of this solution. We're pulling from a pretty dense stack of source material for this.
Oh yeah, very dense. The foundational 1999 and 2000 papers by Thibaut Damour and Alessandro Bonanno, for starters.
Plus some graduate-level lecture notes on EOB dynamics and specific homework problem sets on mapping post-Newtonian expansions.
And we also have detailed optical engineering documentation from advanced LIGO.
Yeah, and we will integrate some recent updates on how modern EOB models incorporate spin, memory, and the tidal effects of neutron stars.
A lot of that draws heavily from groups like the Max Planck Institute. The through line here really is precision.
Absolute precision. We're going to trace how the staggering, almost unbelievable physical precision of the laser interferometers forced theoretical physicists to completely reinvent their math.
They had to entirely change how they calculate the orbital decay of a binary black hole system.
So let's start exactly there. Before we touch a single Hamiltonian or talk about coordinate transformations, we need to establish the physical reality of the experiment.
Because theory doesn't dictate to nature.
Right, nature and the instruments we build to observe it dictate the demands on our theories. And the demands coming from advanced LIGO are, frankly, borderline science fiction.
The physical detector is absolutely where this story has to begin. The experimentalists essentially threw down a gauntlet.
Yeah, advanced LIGO is not just a scaled-up Michelson interferometer.
Not at all. It is a wildly complex, coupled optical cavity system. It's designed to measure a change in distance smaller than a fraction of the width of a proton.
Which is just wild to think about. And to achieve that, they utilize a dual recycled optical configuration. Let's unpack the geometry of that.
Sure, so you have the main laser beam entering the system, hitting a beam splitter, and traveling down two orthogonal 4-kilometer arms.
But you don't just let the light bounce back and leave, you trap it.
You trap it extensively. At the input of the entire system, you place a power recycling mirror.
Okay, so before the light even enters the long arms, you've created a resonant cavity.
Exactly. The goal is to build up the effective circulating laser power. In initial LIGO, the input test masses, the mirrors at the start of those arms, they allowed about 3% of the light to transmit through.
Which already seems small, but for advanced LIGO, the sources note they dropped that transmission down to 0.5%.
Right. They are sealing the arms off even tighter. They are dramatically increasing the finesse of those arm cavities.
So by trapping the light for a longer duration, a single photon bounces back and forth many more times.
Exactly, which gives it more opportunities to be phase shifted by a passing gravitational wave. You are increasing your power gain.
And that beautifully reduces your quantum shot noise at high frequencies, right?
It does. Shot noise is simply the statistical fluctuation of photon arrivals. It's like the optical equivalent of rain hitting a tin roof.
More photons mean a smoother, more predictable signal, but physics always demands a trade-off.
It always does.
If you are trapping kilowatts of continuous wave laser power inside these mirrors, you are going to deposit a massive amount of heat.
And heat causes thermal lensing. the mirror substrates physically deform.
They literally warp.
Yeah, they warp and they change their refractive index, which starts to ruin the fundamental mode of the laser beam.
So to compensate for this massive power buildup, the engineers actually had to lower the gain of the power recycling cavity.
Right, but doing that introduces a new problem. It changes the frequency response of the detector.
Okay, how so?
Well, you end up improving your sensitivity at low frequencies, say around 50 hertz, but you drastically degrade your sensitivity at higher frequencies, up in the several hundred hertz range.
Oh, and that high frequency band is exactly where the gold is.
Exactly.
That's the frequency of the final, most violent milliseconds of a black hole merger. Or, the high-pitched chirp of two neutron stars colliding.
If you lose sensitivity there, you lose the climax of the astrophysical story.
So how do the experimentalists recover that high-frequency sensitivity without melting the mirrors?
This is where they introduce the signal recycling mirror, or SRM.
He placed this mirror at the dark port, right? The output where the laser beams recombine and interfere.
That's the one. By adding this mirror, you create yet another cavity, the signal recycling cavity.
And this is a brilliant piece of engineering because it decouples the storage time of the main laser carrier light from the storage time of the gravitational wave signal sidebands.
Yes, and just to clarify, signal sidebands meaning the tiny frequency shifts imparted on the light by the stretching and squeezing of space-time.
Right. Advanced LIGO operates in a regime known as resonant sideband extraction.
By microscopically detuning the position of that signal recycling mirror, you can actually change the resonance condition for those specific sideband frequencies.
So you essentially pull the signal out of the arms faster than the carrier light.
Exactly, broadening the bandwidth of the detector and recovering that vital high-frequency sensitivity. You can literally tune the detector's peak sensitivity to hunt for specific astrophysical events.
That is just an incredible level of optical manipulation. But the sources from the Max Planck Institute take it a step further into the realm of pure quantum mechanics.
Because even with dual recycling, you eventually hit the standard quantum limit.
Right. The random fluctuations of the quantum vacuum itself start to blind you.
The standard quantum limit is the fundamental balancing act of continuous measurement. As we discussed, if you crank up the laser power, you reduce the phase uncertainty, the shot noise.
Which helps at high frequencies.
Right. But more photons mean more radiation pressure. The photons physically kick the multi-kilogram mirrors, introducing amplitude uncertainty.
This is quantum back action, and it ruins your low-frequency sensitivity. You are completely trapped by the Heisenberg uncertainty principle.
Unless you cheat. Or, well, unless you find a loophole in Heisenberg's math.
Which is my favorite kind of physics. The uncertainty principle says the product of the phase uncertainty and the amplitude uncertainty must be greater than or equal to a certain value.
Right, it doesn't say they have to be equal.
And that loophole is squeezed light. You take the quantum vacuum state entering the dark port of the interferometer, and you manipulate it.
The recent upgrades detailed in the literature involve a detuned optical parametric oscillator.
So you pump a nonlinear crystal with a laser, and through spontaneous parametric down conversion, you create pairs of highly correlated photons.
You are essentially taking the fuzzy, circular blob of quantum uncertainty and squishing it into an ellipse.
You decrease the uncertainty in one variable at the expense of blowing up the uncertainty in the other.
But the real masterpiece of this upgrade is that it is frequency-dependent squeezing.
Because radiation pressure dominates at low frequencies, and shot noise dominates at high frequencies.
Exactly. So a static squeeze state isn't enough. You need the orientation of that quantum ellipse to rotate depending on the frequency you are measuring.
The sources mention a specific metric that is just crazy. At 197 megahertz, the squeezing ellipse rotates by 39 degrees.
Yeah. And this physical rotation drops the quantum noise by 5.5 decibels, exactly where the detector needs it most.
They achieve this rotation using a 300-meter-long filter cavity. It is an awe-inspiring manipulation of the quantum vacuum.
It really is. It evades the standard quantum limit to present a pristine, impossibly quiet background against which we can listen for gravitational waves.
And this brings us back to the theorists and the absolute crisis they were facing in the late 90s.
Because the experimentalists are building multi-billion-dollar quantum vacuum squeezing, dual recycled laser interferometers to clear away the static.
They are handing the theorists a perfectly clean canvas.
But a clean canvas is useless if you don't know what you're supposed to be looking for.
Right. The data analysis of LIGO relies entirely on matched filtering. We have to slide a theoretical waveform template over the data.
a mathematical prediction of what the gravitational wave should look like. If the template matches a signal buried in whatever residual noise remains, the signal pops out.
So if your mathematical template is off, I mean, even by a fraction of a phase, or if the amplitude evolution is slightly wrong, the template won't correlate.
The signal slips right through the net.
It's like building the world's most powerful electron microscope to find a highly specific mutated virus.
Yes, exactly.
If the theoretical biologists give you the wrong blueprint for the virus's shape, you won't recognize it, even if it's dead center on your lens.
And in 1999, the theoretical blueprints were failing spectacularly. General relativity had hit a mathematical wall when it came to predicting the most crucial part of the signal.
The plunge. Let's transition into that failure. Why couldn't we just use the existing math? We had Einstein's field equations. We knew how to model orbits.
To understand the failure, we have to look at the traditional method for solving the two-body problem in general relativity, which is the post-Newtonian, or PN, approximation.
Okay, the two-body problem. We have two black holes, masses m1 and m2, and let's say that they have spins s1 and s2.
They are trapped in a mutual gravitational well, orbiting a common center of mass, radiating gravitational waves, and slowly spiraling inward.
In Newtonian mechanics, this is a solved problem.
But in general relativity, the gravitational field itself carries energy, which generates more gravity. Space-time is nonlinear and self-interacting.
So there is no exact analytical solution for two comparable masses orbiting each other in GR.
Right. So for decades, physicists relied on perturbation theory.
The post-Newtonian expansion. You start with a simple, solved Newtonian orbit, and you add relativistic corrections piece by piece.
You construct a Taylor series. You represent the dynamics, specifically the conservative Hamiltonian, as an expansion in a small parameter.
And the conservative Hamiltonian describes the energy of the orbit ignoring the radiation for a moment, right?
Exactly. And that parameter is typically v over c, the orbital velocity over the speed of light.
Or, equivalently, you can use the gravitational parameter, often denoted as gamma e.
Yes, which is Newton's gravitational constant g times the total mass m divided by the speed of light at c squared times the orbital separation radius r.
Structurally, your real relativistic Hamiltonian looks like a polynomial. You have the Newtonian term plus a 1pn term scaled by 1 over c squared.
Plus a 2pn term scaled by 1 over c to the fourth, and so on.
And as long as your expansion parameter is very small, the higher order terms shrink rapidly to zero, and the math behaves beautifully.
And when the black holes are millions of miles apart during the early adiabatic inspiral, that parameter is indeed tiny.
Their velocity is a small fraction of the speed of light. The gravitational field is relatively weak.
The Taylor series converges. You can predict the orbital phase with high precision.
But the black holes are radiating energy, the orbit is shrinking, and as r gets smaller, the orbital velocity v increases.
The gravitational parameter gamma e grows.
And eventually, you hit a critical geometric boundary in the spacetime, right? The last stable circular orbit, or the ISCO, the innermost stable circular orbit.
This is a fundamental feature of strong field general relativity. In a simple Schwarzschild spacetime, a non-spinning black hole, the effective gravitational potential isn't just a simple inverse square well like in Newtonian physics.
It has a centrifugal barrier that keeps the particle in orbit.
Yes, but at very close distances, the intense relativistic gravity overpowers that barrier.
The potential well develops a lip, and then it just drops off into an infinite pit.
Exactly. As the black holes spiral inward, the stable valley they're orbiting in gets shallower and shallower.
Until it just vanishes.
Right. At the ISCO, the minimum of that valley merges with the maximum of the barrier, and the valley disappears entirely. The stable orbit vanishes.
The bodies cross a dynamical threshold and begin a rapid, irreversible free fall toward each other. This is the plunge.
Now, in standard Schwarzschild coordinates, this ISCO occurs at a separation radius, r equal to 6 gm over c squared.
Okay, so if we plug that radius back into our post-Newtonian expansion parameter, gamma e equals gm over c squared r.
The gm over c squared terms cancel out, and we are left with gamma e equals 1/6.
And this is where the post-Newtonian wall stands. What happens to a Taylor series when your expansion parameter approaches 1/6?
It falls apart. It becomes pathologically inaccurate.
Because a Taylor series, by definition, is a polynomial.
It tries to build a curve by stacking gentle parabolas and cubic shapes on top of each other.
But the plunge phase involves extreme, non-perturbative geometry. You are dealing with asymptotes and sharp phase transitions.
A polynomial simply cannot bend that way.
It's like trying to mathematically describe the shape of a sheer cliff face using only gentle rolling hills. You can stack as many hills as you want, but you will never get a vertical drop.
Exactly. At the ISCO, the post-Newtonian Taylor series either diverges to infinity or it begins to oscillate wildly.
Predicting that the black holes suddenly repel each other or travel backward in time.
It produces absolute nonsense. This was the crisis of the 1990s. The experimentalists were building LIGO, and the theorists couldn't predict the actual merger.
Now, we did have the close limit approximation, right?
I did. If you look at the very end of the merger, when the two black holes have already formed a single highly distorted remnant, you can treat it as a single black hole undergoing linear perturbations.
That's the ring down phase. It rings like a bell, radiating away the deformations until it settles into a smooth, curved black hole. We could calculate that.
Yes, but we had a massive gap. We had the slow in-spiral, described by the P.N. Taylor series, and we had the final ring down, described by perturbation theory.
But the bridge, the violent plunge, and the actual merger was a total mathematical blind spot.
What about supercomputers? I mean, numerical relativity. Just put the Einstein equations on a grid and crunch the numbers.
In the late 90s, numerical relativity was in its infancy. The equations are so non-linearly complex that early computer simulations would simply crash after a fraction of an orbit.
It was vastly too computationally expensive to simulate an entire in-spiral, plunge, and ring-down sequence.
A bridge was desperately needed to connect the analytical regimes.
And that brings us to 1999. Alessandro Bonanno and Thibaut Damour publish a paper that completely redefines the landscape.
They didn't try to fix the Taylor series directly, did they?
No, they realized the entire framework of tracking two separate bodies was the problem. They introduced the effective one-body transformation.
The conceptual leap here is profound. In classical Newtonian physics, reducing a two-body problem to a one-body problem is a standard textbook exercise.
Right. If the Earth and the Moon are orbiting a common center of mass, you don't calculate two separate trajectories.
You shift to the center of mass frame. You define a single test particle with a reduced mass, denoted by mu.
Which is the product of the two masses divided by their sum, m1, m2 over m.
And you have this reduced mass particle orbit, a stationary central mass m, which is the sum of m1 and m2.
It simplifies the math beautifully. The two-body central force problem becomes a one-body problem in a static potential.
So Bonanno and Damour proposed that this exact philosophical shift could be executed in the fully relativistic, strongly gravitating regime.
Yes, they wanted to map the real post-Newtonian relative dynamics of two spiraling black holes to an effective test particle of mass mu.
But obviously the effective particle isn't just orbiting a simple Newtonian point mass anymore.
No. The intense, non-linear gravitational interactions of the two actual black holes are absorbed into the geometry of a deformed, static, spherically symmetric effective metric.
We call this metric G effective mu nu.
Right. The effective test particle moves through this warped background spacetime.
Conceptually, it makes sense. But how on earth do you mathematically execute that mapping? In general relativity, you can't just set the Hamiltonians equal to each other.
No, you can't. We're dealing with coordinate systems that stretch and warp.
If I use one coordinate system for the real two-body problem and a different coordinate system for the effective one-body metric, the Hamiltonians will look completely different, even if they describe the exact same physical reality.
You have hit on the exact obstacle that prevented this from being done for decades. Gauge ambiguities.
General relativity gives you the freedom to choose any coordinate system you want.
But that freedom makes comparing two different mathematical descriptions a nightmare of coordinate artifacts.
So how did Damour and Bonanno bypass the coordinate nightmare?
By seeking inspiration from a completely different branch of physics, This is the hook we mentioned earlier. De Moore looked at quantum mechanics.
Specifically, he was inspired by the work of Brezin, Itzikson, and Zinn-Justin in the 1970s.
Who were studying electromagnetically interacting quantum two-body systems, quantum electrodynamics.
They were trying to calculate the energy states of things like positronium, an electron, and a positron orbiting each other.
Exactly. And in quantum mechanics, instead of trying to map the complex classical Hamiltonians directly, you map the observables. You map the quantized energy levels of the bound states.
I want to make sure I am fully absorbing this because it feels like a massive leap.
It is a massive leap.
They are trying to solve a purely classical macroscopic problem. Two black holes, each millions of times more massive than the Earth, locked in a death spiral.
Yeah.
And to solve it, they borrow the mathematical architecture of Bohr-Sommerfeld quantization, the framework used to dictate where electrons sit in orbitals around an atomic nucleus.
It sounds absurd on its face, but logically, it is airtight. The key is gauge invariance. Energy levels in a bound state are physical observables.
They do not care what coordinate system you use to calculate them, they are absolute.
Exactly. So if you can force the quantum energy spectrum of your real two-body system to perfectly match the quantum energy spectrum of your effective one-body system,
then their underlying classical Hamiltonians are guaranteed to be physically equivalent.
yes, they will be linked by what is called a canonical transformation.
Which is a mathematical mapping that preserves the fundamental structure of the physical phase space, stripping away all the coordinate garbage.
The sources detail how they established this dictionary. They used action angle variables.
Right. They equated the action variables of the two systems, specifically the azimuthal action J, which is the integral of the angular momentum p sub phi over a full orbit.
And the total action N, which incorporates both radial and angular motion.
So by demanding that the real system and the effective system have the same action variables, they forced their energy levels into alignment.
And out of this quantum mechanical theft comes a surprisingly clean algebraic equation, the EOB energy map.
This is the Rosetta Stone of the entire formalism.
The mapping they derived states that the effective energy divided by the reduced mass mu is equal to the real energy squared minus the individual masses squared, all divided by twice the product of the masses.
Structurally, if you look at that equation, it almost looks like a modified Pythagorean theorem, or the law of cosines applied to the relativistic energy momentum vectors.
It's fundamentally a geometric translation between two different spacetimes. That is an excellent way to visualize it.
It translates the energy of a wildly complex, dynamic, self-interacting two-body spacetime into the energy of a single particle in a static, deformed well.
And once you have that energy map, you can invert it to find the Holy Grail, the effective EOB Hamiltonian formula.
Let's examine the structure of that Hamiltonian, because this is where the physics really crystallizes.
The formula is HEOB equals the total mass m multiplied by a square root. Inside that square root, we have 1 plus 2 nu times a quantity, which is the effective Hamiltonian h, effective over mu, minus 1.
Let's break down the parameter nu. This is the symmetric mass ratio, defined as the reduced mass mu divided by the total mass m.
Or equivalently, m1, m2 over m squared. This single parameter is the dial that controls the deformation of our effective spacetime.
Let's play with that dial. What happens to the math if we have an extreme mass ratio in spiral? Say, a supermassive black hole of 1 million solar masses and a tiny stellar mass black hole of 10 solar masses falling into it.
In that limit, the mass m1 is vastly larger than m2. The symmetric mass ratio nu shrinks rapidly towards 0.
And if you look at our EOB Hamiltonian formula, if nu goes to 0, the entire term inside the square root next to it vanishes.
The square root just becomes the square root of 1.
And the EOB Hamiltonian simply equals the total mass m plus the test particle energy. The deformation vanishes.
Exactly. The mathematics smoothly and automatically reduces to the exact known solution for a tiny test particle orbiting in a background Schwarzschild or Kerr metric.
The EOB framework perfectly recovers the test mass limit without any extra tinkering.
Now turn the dial the other way. What if the black holes are identical? Two 30 solar mass behemoths.
That is the equal mass case. Here, the symmetric mass ratio now reaches its absolute maximum value of 1/4.
This is where the deformation of the effective metric is at its most extreme. The effective particle is experiencing the maximum possible nonlinear feedback from the two-body nature of the spacetime.
So we have the scaffolding. But the EOB Hamiltonian formula contains H effective. We don't actually know what H effective is yet.
We have to construct it. We have to execute the canonical transformation at the post-Newtonian level to figure out the actual shape of the deformed metric.
This is where the graduate level algebra gets incredibly intense.
Oh, absolutely. The lecture notes in our source stack walk through this construction at the 1pn order, the first post-Newtonian correction. The goal is to define the effective metric.
A static spherically symmetric metric in general relativity can generally be described by two potential functions. Let's call them A of r for the time component and d of r for the radial spatial component.
At the Newtonian level, A of r is just 1 minus 2m over r, but we need the relativistic corrections.
We expand these potentials into polynomials. A of r becomes 1 minus 2 over r plus a 1 over r squared plus a 2 over r cubed and so on.
And d of r gets expanded similarly with coefficients d sub I. We have to find those unknown coefficients, a 1, a 2, d1, etc.
To do this, we set up an equation that links the real Pn Hamiltonian to the effective Hamiltonian via a canonical transformation generating function. We call this function G1Pn.
A generating function essentially takes your old coordinates and momenta, mixes them up, and spits out new ones that preserve the physics but change the mathematical perspective.
Right. We introduce unknown transformation coefficients into this generating function. Let's call them C1 and C2. We also introduce an energy shift coefficient, alpha 1.
We plug all of this into the Hamiltonian constraint equation, expand everything out using Taylor series in our small parameter, and then we go term by term.
It's a massive exercise in polynomial matching. You gather every term that has an r to the minus 2 dependence and a p squared momentum dependence on the left side of the equation, and you set it equal to the corresponding term on the right side.
You are forcing the algebraic structures to mirror each other perfectly.
It yields a system of coupled algebraic equations. At the 1pn order, you get 5 equations for your 5 unknowns.
Now, general relativity allows for coordinate gauge choices, which means the system is underdetermined. Bonanno and Dahmer used this freedom to make a brilliant simplification,
They chose a coordinate gauge where a 2 and d1 are simply set to 0.
which collapses the algebraic nightmare into a highly solvable system.
Right.
The math spits out the solutions. The energy shift alpha 1 is nu over 2, and the metric coefficients are found.
If you push this grilling calculation to the 2pn order, you find that the higher order effective metric coefficients become A3 equals 2 nu and D2 equals negative 6 nu.
Stop and appreciate what just happened. All the chaotic, self-interacting, highly nonlinear dynamics of two black holes pulling on each other have been completely absorbed.
Packaged into a few simple terms containing nu, sitting inside the A of r and D of r potentials of a static effective metric.
It is breathtakingly elegant.
But I have to push back here.
Please do.
We spent the entire first half of this discussion establishing that the post-Newtonian wall exists because Taylor series explode at the ISCO. Polynomials cannot model the plunge.
Right.
But you just told me that A of r and D of r are constructed as polynomial expansions. We still have a 3 over r cubed and so on.
Yes.
If we just plug this effective metric into our Hamiltonian, aren't we still riding the same broken roller coaster track? Won't the EOB Hamiltonian still diverge when the particle hits the effective ISCO?
Your suspicion is entirely correct. If we stopped here, EOB would be a neat algebraic trick, but it would still fail to model the merger.
Because a polynomial is still a polynomial, even if it's sitting inside an effective metric.
The coordinate transformation alone does not cure the pathological behavior of the strong field regime.
So the infinities are still there. How do we kill them?
We have to mutate the math one more time. This is the second stroke of genius in the 1999 paper, Payday Approximants.
Payday resumation. Let's unpack the mechanics of this because it feels like a mathematical cheat code. What exactly is a payday approximant?
It is a non-perturbative mathematical technique. It takes a standard polynomial Taylor series, which is just a sum of terms in a single line, and replaces it with a rational function.
Meaning a fraction. A ratio of two different polynomials. A numerator divided by a denominator.
Yes. You choose the coefficients of the numerator polynomial and the denominator polynomial such that if you were to perform a Taylor expansion on that fraction, the resulting series would perfectly match your original post-Newtonian Taylor series up to the order you calculated.
Okay, so it contains the exact same physical information as the Taylor series. But why does dividing two polynomials magically behave better at the ISCO than one long polynomial? What is the geometric difference?
The geometric difference is everything. A standard polynomial, by its mathematical definition, can only go to infinity when its variable goes to infinity. It can curve up or down, but it cannot create a vertical asymptote in localized space.
Right, y equals x squared or x cubed, they just keep drifting outward.
But a rational function has a denominator, and a denominator can equal 0.
Oh, wow.
When the variable reaches a value that makes the denominator 0, the function shoots to infinity right there at that specific location. It creates a mathematical pole.
And in strong field general relativity, space-time is defined by extreme geometry. Coordinate singularities, event horizons, these are physical structures that mimic the behavior of asymptotes and poles.
Precisely. A Payet approximant has the mathematical flexibility to model sharp, non-perturbative features that a flat polynomial is too rigid to see.
Earlier, I used the analogy of trying to map a sheer cliff face with rolling hills. The Payet approximant basically introduces the mathematical concept of a vertical wall. To use a different analogy, it's like early 3D video game rendering.
How so?
A Taylor series is like trying to render a perfectly smooth, tightly curved sphere using flat polygons. If the sphere is huge, like the Earlian spiral, the gentle curvature looks fine.
Right, the approximation works.
But as the sphere gets smaller and tighter as we approach the ISCO, the flat polygons can't conform to the geometry. The render breaks down, it looks jagged, blocky, and wrong.
That makes sense.
Payet resolution is like switching your game engine from polygons to calculating true, smooth mathematical curves. The new engine natively understands how to render the extreme geometry without breaking.
That is a phenomenal way to visualize it. By applying Payet resolution to the A of R metric potential, we smooth out the pathologies.
A standard 3PN Taylor expansion of the potential often won't even show a minimum. It predicts no ISCO at all, just a continuous slide.
But the Payet resumed A of R smoothly and stably extends the validity of the metric all the way down to R equals 6gm over c squared, revealing the true ISCO.
And crucially, the sources emphasize that it remains stable past the ISCO. It defines the EOB light ring.
Yes, the light ring is the photon sphere, the absolute point of no return for circular orbits, even for light.
So by establishing this robust geometric boundary, the EOB framework allows the test particle to transition seamlessly from the slow, adiabatic, and spiral.
It can cross the dynamically unstable ISCO and execute a smooth, mathematically stable plunge toward the center. The bound state problem is officially solved.
That is a monumental achievement. But here is where the source material takes a sharp left turn, and it blew my mind when I read it.
Oh, the scattering part.
Yeah. Section 2 of our lecture notes introduces a completely different scenario, post-Minkowskian scattering. We've spent this whole time talking about bound orbits, black holes trapped in a well.
Yes, but the EOB mapping turns out to be far more universal than Debord initially realized. To appreciate this, we need to distinguish between post-Newtonian, or PN, and post-Minkowskian, or PM, approximations.
We established that PN assumes weak gravitational fields in slow motion. Expanding in V over C, what are the rules for PM?
The post-Minkowskian approximation assumes a linear perturbation to flat, empty spacetime, Minkowski space. But critically, it does not restrict velocity.
So a first post-Minkowskian, or 1 PM, calculation is valid to all orders in velocity V over C, up to the speed of light.
It is only expanded in terms of the gravitational constant g.
So it demands weak gravity, but you can be moving as fast as you want, which makes it the perfect mathematical tool for unbound systems. Scattering events.
Exactly. Imagine two black holes flying toward each other from deep space at a significant fraction of the speed of light. They aren't trapped. Their velocity squared is much larger than the gravitational potential gm over r.
They just deflect off each other and fly away.
Now consider the scattering angle, which we denote as chi. If we calculate the 1 PM scattering angle chi as a function of E and L in the center of momentum frame of these two real massive bodies, we get a specific formula depending on their total energy and angular momentum.
And we want to see if the EOB trick works here. So we set up a test body scattering off a fixed background metric and calculate its scattering angle chi sub t as a function of E sub t and L sub t.
We stipulate that the angular momentum must be the same, so L equals L sub t. Then we ask the crucial question, what must the relationship be between the real energy E and the effective test energy E sub t to guarantee that the two scattering angles match perfectly?
You do the algebra, you match the angles, and you solve for the energy map.
And what you find is nothing short of magical. The energy mapping required to perfectly match the 1 PM scattering angles is E sub t over mu equals E squared minus M1 squared minus M2 squared, all divided by 2 M1 M2.
Wait, That is the exact same equation. That is the identical algebraic structure we derive from the quantum-inspired bound state canonical transformation using action variables.
It is the exact same EOB energy map.
That is profound. It's like discovering that the physics governing two sports cars narrowly missing each other in a high-speed highway near miss is governed by the exact same underlying mathematical Rosetta Stone as two cars trapped endlessly circling a roundabout.
It is a stunning revelation. It proves that the EOB mapping is not merely a clever algebraic trick designed to patch a broken Taylor series for inspirals.
It demonstrates that the EOB energy map captures something fundamentally deep and universal about the nature of relativistic gravity itself.
The mapping is invariant. It seamlessly bridges the physics of bound states, orbits, and unbound states, scattering.
It hints at a hidden geometric structure in the Einstein equations that we were previously blind to. Okay, I need to take a breath because that's beautiful theory. But we have to bring this beautiful theory back to reality, back to LIGO.
Yes, the experimentalists are still waiting for their waveform template.
Right. And everything we have built so far, the energy maps, the canonical transformations, the Pade-resumed potentials, all of it describes the conservative dynamics.
A Hamiltonian, by definition, conserves energy.
So if we simulate our EOB particle right now, it will just circle the effective black hole forever. It will never merge.
We need a drain in the bathtub. The real black holes are losing massive amounts of energy and angular momentum to gravitational waves. We must incorporate dissipation.
We need to inject a radiation reaction force into our pristine, conservative Hamiltonian system.
We denote this radiation reaction force as F hat sub phi. To see how it alters the system, we have to look at the equations of motion for the particle in phase space.
We define the state of the system using 4 variables: the radial distance r, the tortoise conjugate momentum p sub r star, the orbital phase angle phi, and the angular momentum p sub phi.
The lecture notes break this down. The first 3 equations, which dictate how the radius, the radial momentum, and the orbital phase change over time, are derived purely by taking the partial derivatives of the EOB Hamiltonian.
These equations drive the conservative orbit.
But the 4th equation is where we introduce the drain. The time derivative of the angular momentum, dp sub phi over dt, is no longer 0. We set it equal to the radiation reaction force, F hat sub phi.
This force acts like a continuous friction, bleeding angular momentum from the system, forcing the particle to slowly spiral deeper into the effective potential well.
Exactly.
But hold on, just like the conservative Hamiltonian, the energy flux, a formula we use for how much energy is carried away by the waves, was also originally derived using a post-Newtonian Taylor series.
Which means it too will explode at the ISCO.
Exactly. If the drain clogs or explodes right when the water is swirling the fastest, our plunge model still fails.
You are absolutely correct, which is why the flux function must also undergo rigorous resumation. De Moore, Iyer, and Satyaprakash pioneered this. They didn't just Pade-resume the whole thing blindly.
They factored the flux into its constituent physical components. What does factoring it achieve?
It isolates the physics. The flux is separated into a leading order Newtonian prefix, the higher order post-Newtonian corrections, and complex tail effects.
Tail effects, meaning gravitational waves bouncing off the background curvature of space-time and interacting with themselves.
Yes, by separating these components and resuming them individually, they constructed an energy drain that remains stable, smooth, and physically realistic all the way down to the plunge.
Okay, so we have a smoothly resumed conservative body and a smoothly resumed energy drain. The particle crosses the ISCO and begins the plunge.
But the plunge is incredibly violent. The black holes are falling toward each other at an accelerating rate.
The phase space trajectory is going to shift radically. How do we ensure the math doesn't glitch out right before they touch?
That requires the introduction of what we call next to quasi-circular, or NQC, corrections.
NQC. Let's spend some time on this, because for a grad student modeling this, NQC terms are essentially analytical shock absorbers. What physical reality are they trying to capture?
Think about the shape of the orbit. During the millions of years of the adiabatic inspiral, the orbits are essentially quasi-circular. The black holes are moving very fast tangentially, but their radial velocity, how fast they are moving directly toward each other, is tiny.
So in phase space, the radial momentum p sub r is effectively 0 compared to the massive angular momentum p sub phi.
Exactly. The standard PN expansions are built on this assumption of quasi-circularity. But when the binary crosses the ISCO and the plunge begins, that assumption shatters.
The radial momentum p sub r spikes dramatically. The black holes are in free fall.
The plunge is no longer circular, it's a dive.
So NQC corrections are specifically designed analytical terms added to both the waveform amplitude and the flux equations to account for this violent radial motion.
Mathematically, they are constructed using terms proportional to p sub r and its time derivatives.
Because they need to vanish during the circular inspiral when p sub r is 0, but turn on strongly during the plunge.
Precisely. They act as a mathematical bridge. We need the waveform generated during the plunge to smoothly connect to the final stage of the merger.
We determine the coefficients of these NQC terms by demanding continuity. We enforce that the amplitude of the EOB waveform and its time derivative perfectly match the expected conditions at a specific moment. The merger time T sub m.
Merger time T sub m. This is the moment the two event horizons touch and merge into a single, highly deformed, violently vibrating Kerr black hole.
The effective one-body particle has essentially reached the center of the potential well. The plunge is over.
And a new physical regime begins. The ring down.
So how does the EOB formalism model the ring down?
It doesn't model it internally, it attaches it externally through a mathematical matching process. The final Kerr black hole radiates energy through quasi-normal modes, or QNMs.
It rings like a struck bell, with specific frequencies and damping times dictated purely by the final mass and spin of the black hole.
The no-hair theorem in action. The complex two-body history is forgotten, leaving only a bald, spitting sphere.
To construct the complete, full and spiral-to-ring-down waveform, which is what LIGO actually needs, we use a step function, specifically the Heaviside step function, denoted by theta of t.
The sources provide the exact construction. HEOB of t equals theta of t sub m minus t times the inspiral plus plunge waveform plus theta of t minus t sub m times the ring-down waveform.
It is a mathematical switch. For all time t before the merger time t sub m, the first step function is 1 and the second is 0.
The EOB framework actively computes the trajectory, applies the NQC shock absorbers, and generates the waveform.
The moment t passes t sub m, the switch flips. The EOB trajectory turns off, and the analytical superposition of the final Kerr black hole's quasi-normal modes turns on.
The step function literally glues the two solutions together.
Let's be honest for a second. We have canonical transformations mapping bound states based on quantum mechanics. We have Padet-resummed Hamiltonians to fake an ISCO. We have a separately resummed flex for the drain. We sprinkle in NQC shock absorbers when things get bumpy.
Right.
And then we literally use glue, a step function, to attach the ring down.
It sounds like a patchwork quilt.
It sounds like Frankenstein's monster. I mean, it is incredibly clever, but it is an analytical construction built on a tower of assumptions and resumation tricks. How does this patchwork actually hold up against reality?
Or, barring reality, how does it hold up against the brute force truth of supercomputers solving the raw, unadulterated, nonlinear Einstein equations?
That is the ultimate trial by fire. And answering that question is what propelled EOB from a clever theoretical paper in 1999 to the absolute, undisputed workhorse of modern gravitational wave astronomy.
EOB embraced the supercomputers.
You were talking about the synergy with numerical relativity, or NR.
Yes. EOB was never meant to replace numerical relativity. In the modern era, they operate in a state of perfect symbiosis.
Explain that dynamic. Why do we need both?
Because numerical relativity is exact, but it is agonizingly slow. By the mid-2000s, breakthroughs in gauge choices allowed supercomputers to finally simulate a binary black hole merger without crashing.
But solving the full Einstein equations on a three-dimensional grid is computationally grueling. A single simulation of a merger can take weeks or even months of supercomputer time.
And as we established, LIGO needs millions of waveform templates to slide over their squeezed light data to find a match. You cannot wait a month for one template.
Exactly. EOB, on the other hand, is lightning fast. Because we reduced the complex spacetime grid into a set of ordinary differential equations for a single particle, a standard computer can solve an EOB trajectory in a fraction of a second.
But as you pointed out, EOB is built on approximations.
It has flexibility. Remember earlier we talked about finding the coefficients for the effective metric, a 3, D2, etc. We only knew the exact analytic solutions up to a certain post-Newtonian order.
The higher order terms, the 4pn, 5pn, and 6pn interactions, were theoretically unknown.
In the Padet resumation of the A of R potential, we represent these unknown higher order contributions with parameters like a 5 and a 6. These are flexible, unconstrained parameters in the EOB model.
I see where this is going. We use the supercomputers to find the answers to the test.
Precisely. The modern EOB framework is semi-analytical. We generate a sparse grid of exact numerical relativity simulations, a few dozen highly accurate, months-long calculations spanning different masses and spins. These serve as our absolute ground truth.
And then we take our fast, flexible EOB model and we run it alongside the NR data. We fine-tune those unknown parameters, a 5, a 6, and certain NQC coefficients until the EOB waveform perfectly overlays the NR waveform.
It is the ultimate algorithmic compression of general relativity. We use the slow supercomputers to chart the true north on the map. We then calibrate our lightweight EOB compass against those true north points.
Once calibrated, the EOB compass can instantly and accurately navigate anywhere on the vast parameter space of masses and spins, generating millions of templates on demand.
And the fidelity is astonishing. The sources cite a metric called median unfaithfulness, which measures the mathematical disagreement between the EOB template and the exact NR simulation.
Calibrated EOB models consistently achieve an unfaithfulness below 3 × 10⁻⁴.
That is an error rate of less than 0.03%. That is well below the residual noise threshold of advanced LEGO. The theoretical template is no longer the bottleneck, it is flawless.
And this calibration framework allowed EOB to evolve rapidly. The modern extensions discussed in our sources show that EOB is no longer just for simple, non-spinning black holes on circular orbits. It has become a beast.
The complexity that modern EOB models can handle is staggering. Take spin, for example. Real black holes spin, and their spins might not be aligned with the orbital axis.
This causes the entire orbital plane to precess, wobbling like a top as it spirals in.
How does EOB handle two separate wobbling spins if it's supposed to be a one-body framework? The effective particle only has one spin. How does it feel the interaction of two spinning black holes?
It's a brilliant extension of the mapping. You don't just give the test particle a spin, you also encode the combined spin interactions into the warped background spacetime itself.
The modern Hamiltonian incorporates full spin precession, including spin orbit and spin couplings up to 4p order.
And it is strictly designed to ensure that if the mass ratio drops to 0, it perfectly recovers the exact precessing dynamics of a particle in a rotating curve metric.
The geometry remains consistent. The sources also mention orbital eccentricity.
Yes, not all binaries circularize completely before they merge. Eccentricity drastically complicates the phase space. The radial momentum isn't just 0 during the end-spiral, it oscillates.
The EOB framework has been expanded to model these eccentric elliptical plunges, which is vital for detecting binaries formed dynamically in dense star clusters.
It even models gravitational memory effects. This is where the passage of a gravitational wave leaves a permanent, direct, current static deformation in the local spacetime.
The distance between two free-falling objects is permanently altered after the wave passes. Modern EOB models incorporate both oscillatory and DC memory.
But perhaps the most crucial modern extension involves moving beyond black holes entirely. EOB is extensively used to model the collision of binary neutron stars.
Now that introduces a massive complication. Black holes are point masses, geometrically speaking. They are rigid. But neutron stars are made of matter, incredibly dense matter, but matter nonetheless.
As they spiral toward each other, their immense gravities pull on each other.
They raise tides. Just as the moon raises tides on the Earth's oceans, a neutron star will physically bulge and squash under the gravitational pull of its companion.
And a squashed, elongated neutron star creates a different gravitational potential than a perfectly spherical one.
This tidal deformability, quantified by parameters known as love numbers, will alter the rate at which they spiral inward. The phase evolution of the gravitational wave changes.
How on earth do you put a squishy neutron star into the EOB Hamiltonian?
You modify the effective metric potentials again. The tidal deformations introduce new, high-order 1 over r to the 5th and 1 over r to the 6th terms into the A of r potential.
The EOB framework seamlessly incorporates these leading and subleading tidal effects, including quadrupole, which is squashing, and octupole, pear-shaped deformations, as well as spin-induced deformations.
By measuring how the gravitational wave phase deviates from a pure black hole EOB template, we can physically measure the tidal deformability of the neutron star. We are using EOB to determine the equation of state of nuclear matter in the core of a dead star.
It demonstrates the supreme adaptability of the formalism. What started as a desperate algebraic trick to bridge a mathematical gap has matured into a comprehensive, universal framework for understanding compact binary coalescence in all its forms.
Let's step back and look at the sheer scale of the intellectual journey we have just charted. We started with the raw, uncompromising, experimental necessity.
Advanced LIGO, a machine manipulating the quantum uncertainty principle itself with rotating squeezed light to evade the standard quantum limit, demanded theoretically flawless templates.
But the theorists were blocked by the post-Newtonian wall. The classical Taylor series expansions of general relativity violently diverged precisely at the ISCO, right when the physics mattered most.
And the solution to that classical crisis was a brilliant, almost heretical theft from quantum mechanics.
De Moore and Bornono realized that by equating the bound state action variables, they could map the quantized energy spectra.
This established a gauge-invariant dictionary, allowing them to map the chaotic two-body problem onto a single effective particle moving through a highly deformed metric.
We waded through the grueling algebra of canonical transformations to build that metric. We then applied Pade resumation, replacing rigid polynomials with rational functions, to mathematically smooth out the infinities, model the poles, and reveal the stable EOB light ring.
We proved the deep geometric universality of this energy mapping by showing it identically predicts post-Minkowskian high-speed scattering events.
We injected reality into the Hamiltonian by adding a resumed radiation reaction flux to drain the energy. We built NQC analytical shock absorbers to keep the phase space trajectory stable as the radial momentum spiked during the plunge.
We glued the final Kerr ring down to the plunge with a step function.
And finally, we unleashed the supercomputers, using exact numerical relativity simulations to calibrate our flexible EOB parameters, creating the ultimate lightning-fast algorithmic compression of Einstein's equations.
It is a breathtaking synthesis of physics, combining perturbation theory, quantum mechanics, numerical simulation, and optical engineering.
It stands as a testament to the fact that theoretical physics is rarely a straight line. Sometimes you have to borrow architectures from completely different domains to see the true geometry of the problem.
Which leaves us with one final provocative thought.
And this is something for you to mull over as you close your thesis notes or step away from the lab today. We used a trick from quantum mechanics, the mapping of bound state energy levels via action variables, to solve a purely macroscopic classical problem of massive black holes merging.
A pragmatic theft that yielded incredible results.
But is it just a pragmatic mathematical coincidence? Modern physics is currently paralyzed by the struggle to unite general relativity and quantum mechanics into a single, cohesive theory of quantum gravity.
Could the shocking success of the effective one-body formalism be a hint?
A hint at a deeper structure, exactly. If the mathematical structures and energy maps of quantum-bound states so perfectly, cleanly mirror the classical relativistic orbits of black holes, perhaps they aren't so different after all.
Perhaps the ultimate bridge between the subatomic quantum world and the cosmic, space-time bending macroscopic world is already hiding right in front of us, buried deep in the algebraic equations we use to listen to the stars.
It suggests an underlying geometric unity to nature that we are only just beginning to scratch the surface of. The math is trying to tell us something.
Keep your eyes on the math. Question the assumptions.
Because when the continuous, predictable curve of classical determinism snaps, sometimes you have to borrow the weird quantized rules of the atom to fix the roller coaster track. Thanks for diving deep with us.
So imagine you're trying to measure the width of a single atom.
Okay, sounds hard enough already.
Right. But now imagine trying to do that exact measurement while you are standing on a trampoline.
Oh, wow.
And the trampoline is in the middle of a hurricane.
That's a great visual.
Yeah. And just to make it completely impossible, your tape measure is made entirely out of light.
Yeah, that basically captures the absolute just engineering nightmare of advanced LIGO.
Right. Welcome to the deep dive, everyone. We are so glad you're here. Today, our mission is to explore the mind-bending technological leaps that transformed the initial LIGO detector into advanced LIGO.
And this is a fun one because it fundamentally breaks how we usually think about scientific instruments.
Oh, totally.
Yep.
I mean, usually when you build a tool like a microscope or a telescope, what's the first thing you do?
You bolt it down.
Exactly. You lock it to the earth because rigidity is comfort, you know.
Right, you want your baseline to be totally static, because if the instrument itself is moving around, you can't trust what you're seeing through the lens. The Earth is supposed to be the anchor.
But, and this is what we found in this huge stack of sources we're looking at today, which, by the way, includes technical design documents, prototyping reports from Caltech and MIT, plus some really dense physics lectures the moment you step into the world of gravitational wave astronomy. That solid ground turns into your worst enemy.
It really does. The Earth isn't an anchor at all. It is a chaotic, vibrating, noisy mess.
So we're going to take those dense schematics and really get into the gears of how this machine pulls off what frankly sounds like literal science fiction.
Because initial LIGO, the first version, was undeniably an engineering marvel. I mean, it proved the concept.
Yeah, it proved we could build these giant L-shaped laser interferometers with 4-kilometer-long arms and, actually keep them operational.
Right. But it was really only a proof of concept. The entire goal of the advanced LIGO upgrade was to increase the strain sensitivity of the detector by a factor of 10.
And I want to pause on that for a second, because if you're just looking at the numbers, a factor of 10 might sound like just an incremental upgrade. Like, oh, it's 10 times better.
Oh, but in astrophysics, it changes everything.
Right. Explain why that is for everyone, because the math here is so crucial.
So if you increase your sensitivity by 10, you aren't just seeing 10 times more stuff. Because space is three-dimensional, the volume of the universe that you can observe scales as the cube of your sensitivity.
The cube. So it's 10 times 10 times 10.
Exactly. So a 10 times improvement in reach actually means you are detecting 1,000 times more of the universe.
1,000 times more volume. That completely changes the game.
It takes the detection of a gravitational wave from being this once-in-a-lifetime miraculous anomaly and turns it into a routine astronomical observation.
Yeah, the sources mentioned it's the difference between staring at the sky for a decade, just praying to catch a single merging black hole, versus studying entirely new populations of them every single week.
Right. But getting to that 1,000-fold increase in volume, that required an all-out war on the fundamental laws of physics.
Because they couldn't just build a bigger tube or plug in a stronger laser. They had to fight nature at every single level.
Because to measure a gravitational wave passing through the Earth, you have to measure a change in distance across that 4-kilometer stretch of land that is a tiny fraction of the width of a proton.
Which brings us right back to the trampoline and the hurricane.
Yep. The vibration problem.
Before you can even turn on a laser to measure a fraction of a proton, you have to deal with the fact that the ground underneath this billion-dollar machine is violently shaking, constantly.
So how do you stop the environment from ruining the measurement?
Right. You have to isolate the detector from the planet it sits on.
Which is wild to think about.
It is. Now, initial LIGO used passive isolation, basically stacks of springs and specialized rubber. It dampened the shaking, kind of like the shocks on your car.
Right, but advanced LIGO threw that completely out the window. They introduced an active 6-degree of freedom pre-isolation system.
And when I was reading through the technical documents, the only way I could visualize this was like giant building-sized noise-canceling headphones.
Oh, that is actually an excellent way to conceptualize it.
Yeah.
If you think about how noise-canceling headphones work, they have a microphone on the outside listening to the ambient room noise.
Right, catching the sound before it gets to you.
Exactly. Then the internal processor calculates the exact inverse of that sound wave and plays it into your ear to cancel out the noise before it hits your eardrum.
So the waves just flatten each other out.
Yes. The advanced LIGO active isolation system does exactly this, but physically, with massive chunks of metal and hydraulics.
That is so cool. And the scale of the ambient noise they are fighting is what really got me. We aren't just talking about local earthquakes, right?
Oh, no, not at all. The observatories have this massive physical environmental monitoring system. They have seismometers scattered everywhere, and they are picking up microseismic activity that you and I could never, ever feel.
The sources called it the microseismic peak.
Yes, the microseismic peak is a constant thorn in the side of these engineers.
And one of the primary sources of that ground motion, which I found so surprising, is ocean waves.
It's incredible, isn't it?
Even though the observatories are located far inland, we're talking Washington State and Louisiana, when large ocean waves crash against the continental shelf, they send acoustic vibrations rippling through the Earth's crust.
Right, at around 0.15 hertz.
And that actually causes the ground beneath the detectors, miles and miles away, to roll and vibrate by several micrometers.
Which doesn't sound like much.
A micrometer sounds tiny to us.
Yes.
But when you are hunting for a proton-sized displacement, a micrometer is basically an apocalyptic earthquake.
Exactly. And then as if the oceans weren't enough, you throw in tidal motion.
Wait, like the ocean tides?
No, the literal gravitational pull of the moon passing overhead. It stretches and compresses the Earth's solid crust, shifting the ground by hundreds of micrometers over a period of hours.
So the ground is basically breathing.
Yes. So the seismometers listen to all of this. The ocean waves, the tidal shifts, the wind pushing on the buildings, even a truck driving on a highway 5 miles away.
And they feed all that data into a central computer.
Right, and the control loops calculate the exact counter motions required. Then, using incredibly precise hydraulic actuators, the system physically moves the entire structural platform in real time.
In all 6 degrees of freedom. Up, down, left, right, pitch, yaw, roll.
Exactly, to perfectly oppose the ground motion. They are essentially flying the instrument inside the vacuum chamber to keep it perfectly still relative to the universe rather than relative to the Earth.
Which is just, my brain struggles to even picture that.
Yeah.
And the calculation speed required to pull that off without introducing latency is staggering.
It has to be instantaneous.
Right, because if the computer takes even a millisecond too long to calculate the counterpush, you aren't canceling the vibration anymore. You're just pushing at the wrong time and adding a completely new vibration.
You just make it worse.
But here's the thing. Even with this actively stabilized, hydraulically flying platform, you can't just bolt your mirror to it.
No, you still have to suspend it.
Initial LIGO hung its mirrors from a single pendulum, just a wire with a weight at the bottom. But advanced LIGO uses a quadruple pendulum.
4 pendulums.
4 pendulums stacked in a chain, one hanging from the other, with the main mirror at the very bottom. It's a design they borrowed from the GEO 600 detector.
And we should clarify here that the active hydraulic isolation we just discussed is primarily dealing with low-frequency, large-scale motions. The quadruple pendulum is the next line of defense, targeting the higher frequencies.
Right, and it incorporates 3 stages of miraging steel blade springs, specifically designed for vertical isolation.
Let's talk about the miraging steel for a second, because that isn't something you're going to find at your local hardware store.
No, definitely not. It's a highly specialized alloy. They remove the carbon, which usually is what makes steel brittle, and use elements like cobalt and molybdenum to create these intermetallic compounds.
Which gives you the elasticity of a spring, but with the yield strength of literal military-grade armor plating.
And they need that, right? Because a standard pendulum only really isolates you from side-to-side motion, but the ground is also bouncing up and down.
Exactly. So those massive steel blades act like the heavy-duty shocks on a truck to absorb that vertical bounce before it travels down the chain.
But the horizontal isolation is where this quadruple pendulum design really shines. The sources describe it as a mechanical low-pass filter.
Right. And if you're trying to picture a mechanical low-pass filter, just think about holding a piece of string with a heavy weight tied to the bottom.
Okay, I'm picturing it.
If you move your hands side to side very slowly, a low-frequency motion, the weight just follows your hand perfectly. The motion passes right through the string.
Got it.
But if you start shaking your hand back and forth frantically at a high frequency, the weight barely moves at all.
Oh, because the string just kind of wiggles and absorbs the rapid changes in direction, and the heavy mass just stays mostly still.
Exactly. The fast, high-frequency shaking is filtered out. That is the exact principle of a low-pass filter.
So a single pendulum naturally reduces ground motion at frequencies above its resonant frequency.
Yes, but when you chain 2 pendulums together, you don't just add their filtering capabilities, you multiply them.
Oh, wow.
And when you chain 4 together, the attenuation becomes exponential.
The math on this in the design documents is completely wild. The 4 stages of the advanced LIGO pendulum attenuate ground motion by 7 orders of magnitude at frequencies above 10 hertz.
7 orders of magnitude.
That is 10 million times less vibration. So by the time any physical shaking travels down through the top mass, the second mass, the third mass, and finally reaches the bottom mirror, any high-frequency shaking from the Earth has been entirely deleted.
It's gone. In the horizontal direction, that bottom mirror is effectively a free-floating mass in space.
Just hanging there, decoupled from the local environment.
It responds only to the stretching and squeezing of space-time itself.
Okay, and this is typical for these engineers, they still weren't satisfied.
Never.
Which brings us to one of the most stunning details in this entire deep dive. The final stage of this quadruple pendulum, the part that actually holds the main 40-kilogram mirror, does not use steel wires.
No, it doesn't.
It uses fused silica fibers. They hang a 40-kilogram block of solid glass from 4 strands of pure glass that are only 0.4 millimeters thick.
It is a phenomenal achievement in material science. It really is.
It sounds so fragile. Why on earth would they abandon steel for the final stage?
To understand why, we have to talk about thermal noise.
Okay, so I know thermal noise is fundamentally just heat. It's the ambient jiggling of atoms in any material, right?
Yes.
But are we really saying that room temperature heat is enough to physically move a 40-kilogram mirror and ruin a measurement?
Well, on the macroscopic scale, no, you wouldn't see it with your eye. But at the quantum scale, yes, absolutely.
Wow.
Even at room temperature, the atoms inside a metal wire are vibrating furiously, and metal has a lot of internal friction. So as those atoms jiggle, they rub against each other, dissipating energy.
And that creates a physical vibration.
Yes. This internal mechanical friction creates a chaotic, humming vibration, a noise floor, right in the 10 to 100 hertz frequency band.
And let me guess, that is the exact frequency band where LIGO is trying to listen for the in-spiral of black holes.
Unfortunately for us, it is the exact band.
So a steel wire is literally humming like a plucked guitar string,
Yeah,
purely from the ambient heat of the room.
precisely. It's singing to itself. And to get rid of that hum, you need a material with incredibly low internal friction.
Which is where the glass comes in.
Right. Fused silica, which is just very pure glass, has a remarkably high Q factor or quality factor. It rings incredibly purely, meaning its internal friction is near zero.
So they drew these 0.4 millimeter fused silica fibers to hold the mass. But they didn't just tie them or clamp them to the mirror,
Right.
because a knot or a clamp would rub and create friction.
Exactly. Any mechanical joint creates friction, so they chemically welded them.
Using hydroxide catalysis bonding.
Yeah.
This process is so fascinating. The notes say you can't use glue because glue introduces friction and thermal noise.
Right. Glue is out.
Well, they take this specially formulated chemical droplet containing hydroxide ions, and they place it exactly between the perfectly polished glass fiber and a small glass ear that's on the side of the main mirror.
And then they just wait.
Yeah. The hydroxide essentially eats into the glass network on both sides. And as the water evaporates, the silicon and oxygen atoms form brand new covalent bonds directly across the gap.
The two separate pieces of glass literally fuse into one single continuous molecule.
That is insane. They create what is called a monolithic suspension.
Because structurally, it behaves as if the suspending fibers and the massive mirror were just carved out of a single solid block of glass.
Because there are no joints, no screws, no clamps.
There is nowhere for mechanical friction to hide, so the resonant frequencies of this monolithic structure get pushed way, way up, safely out of the crucial 10 Hz detection band. It radically reduces the thermal noise limit.
But reading the prototyping reports from Caltech, you realize getting this monolithic design to actually work was a brutal process of trial and error.
Oh, I'm sure it was an absolute headache.
There's this specific story in the notes about the anomalous tilt issue that really highlights why metal was ultimately doomed anyway.
Right, the hysteresis problem.
Yeah. During earlier prototypes, when they were still trying to use metal wires, the engineers found that if the suspended mass accidentally got bumped or tilted, it wouldn't return to perfect dead center. It would just stay slightly tilted.
And that is the nightmare of hysteresis in metals.
Can you explain hysteresis for us? The paperclip analogy helped me understand it.
Oh, the paperclip is perfect.
Yeah.
If you bend a paperclip back and forth a few times, it doesn't snap back to being perfectly straight, right?
It gets bent out of shape.
The metal has an internal memory. The atomic lattice physically deforms and gets stuck there. That internal friction prevents it from returning to a state of perfect equilibrium.
Okay, so now imagine you have a perfectly aligned interferometer,
Right.
and a tiny environmental bump causes the metal suspension wire to slightly deform. The mirror slowly drifts out of alignment because the metal wire remembered being bumped.
And you'd lose your lock on the laser constantly. You'd never be able to run an observation.
But fused silica does not suffer from that kind of hysteresis.
Not at all. At an atomic level, glass is an amorphous solid. If you bend a glass fiber, it either bends elastically and returns perfectly with mathematically precise exactness to its original position, or it violently shatters. There is no in-between.
Wow.
There is no internal memory to drift out of alignment. It's either perfect or it's broken.
Which means the engineers assembling these monolithic suspensions had to handle 40-kilogram glass mirrors hanging from 0.4 millimeter glass threads with a level of care that borders on surgical.
One wrong move, one tiny overextension, and the fiber just snaps. And you have to start the chemical bonding process all over again.
But that fragility is the exact price you have to pay for perfect stillness.
It's the only way.
Okay, so if we zoom out for a second, we have actively canceled the ocean waves using giant hydraulics.
Check.
We have filtered out the high-frequency vibrations using a 4-stage exponential mechanical filter,
Yep.
and we have stopped the ambient room temperature from humming by building a monolithic glass sculpture.
We have perfectly isolated the mirror from the Earth.
Right. But isolating the mirror is only half the battle. Because if you get it perfectly still, you run into the next wall of physics, which is the mirror itself, the end-test masses.
And this is where we have to look at how we are actually extracting the measurement from the machine.
Advanced LIGO significantly increased the mass of these main mirrors from the initial design. They are now massive cylinders of fused silica weighing 40 kilograms each.
Which is heavy.
Right, but when I first read this, my intuition completely rebelled against it.
Why is that?
Because if your entire goal is to measure the tiniest, fainter-than-faint push from a gravitational wave rippling across the universe, shouldn't the mirror be as light as a feather? Like, if a wave is weak, wouldn't a lighter mirror be easier for the wave to physically move?
It is a completely logical assumption. If we were purely measuring gravity in a dark void, a lighter mass would indeed be more responsive.
But we aren't in a dark void.
No, we have to measure the position of that mirror, and to do that, we are blasting it with a laser. And this introduces a massive paradox. Because light carries momentum.
Light has physical force. So if you shine a laser at a feather, the light physically pushes the feather.
Exactly. When photons hit the surface of the mirror and reflect back, they impart a physical kinetic force onto the glass. This is known as radiation pressure.
Okay, radiation pressure.
And if the laser were a perfectly smooth, uniform stream of energy, it wouldn't be a huge problem. It would just provide a constant, steady push. You could just calibrate for it.
But a laser isn't smooth, is it?
No, it is made of individual quantum packets of energy photons. The arrival of those photons is statistical. There are tiny, random fluctuations in the number of photons hitting the mirror at any given nanosecond.
So the laser is actually buffeting the mirror.
Yes, like wind hitting a sail on a gusty day.
Wow, okay. And that random buffeting creates radiation pressure noise, which fundamentally shakes the mirror and masks the gravitational wave signal.
Especially at the lower frequencies. So how do you stop your own measuring tool from knocking your perfectly isolated mirror around?
You give the mirror more inertia, you make it heavier.
Exactly. A 40-kilogram mass is essentially too heavy for the fluctuating wind of the laser to push around erratically. It resists the buffeting, which violently lowers the radiation pressure noise and cleans up the low-frequency sensitivity band.
That is such a brilliant workaround. But making it heavier is just the structural solution. The optical requirements for this block of glass are where the manufacturing process truly starts to sound alien.
Oh, the polish alone is unbelievable.
Right, I was geeking out over the physical perfection of these objects. The source documents note there was initially a fierce debate in the scientific community about what material to use for these test masses.
Yeah, some argued for high-Q sapphire.
But fused silica ultimately won out and became the baseline for advanced LIGO. So these mirrors are 34 centimeters in diameter, roughly the size of a large pizza, and they're 20 centimeters thick.
And because they are pure fused silica, they are completely transparent.
Right, they're glass.
So to make them highly reflective at the specific infrared wavelength of the laser, they are coated with a multi-layer stack of alternating materials, specifically silicon dioxide and tantalum pentoxide.
Okay, but the metric that truly breaks my brain is the polish itself. The documents state that the surface of the mirror is super polished to an accuracy of lambda over 800 over the central 10 centimeters.
That's a very technical way to say it's incredibly flat.
To put that in human terms, the surface accuracy is about 1 nanometer root mean square. 1 nanometer.
It's hard to even conceptualize how small a nanometer is.
The sources get a great analogy. If you took this pizza-sized mirror and scaled it up so it's the size of the entire planet Earth, the tallest mountain on the surface of the glass would be less than an inch high.
It is the most perfect surface ever created by humans.
But why do they need to go to that extreme? I mean, a standard high-end telescope mirror isn't nearly that perfect.
Because a standard telescope is just collecting light to form a blurry image. LIGO is relying on phase noise. The laser beam bouncing between these mirrors is carrying the highly sensitive phase information that dictates our entire measurement.
Okay, so if the mirror has even a microscopic imperfection, like a single bump a few nanometers high,
it triggers a cascade of catastrophic failures.
Let's walk through those failures because the notes highlight 2 major ones.
The first is scatter. When the perfectly collimated laser beam hits that microscopic bump, a tiny fraction of the light scatters out of the main path.
So you're losing light.
Right, that is an immediate loss of optical power, which degrades the sensitivity. But it also introduces the risk of scattered light hitting the metal walls of the vacuum tube, bouncing around and re-entering the beam path later.
which creates terrifying acoustic noise in the data. It's like trying to see a crystal clear reflection in a mirror that has a tiny dusting of flour on it, right? The light scatters, the contrast drops, and the image just gets fuzzy.
Exactly. The interference fringe gets washed out. But the second and far more dangerous consequence of imperfect polish is absorption.
Right, because the coatings are magic.
No, the tantalum pentoxide coatings are designed to reflect light, but they aren't perfect. If an imperfection or a tiny contaminant causes the mirror to absorb even 1 part per million of the laser light, that absorbed optical energy immediately turns into heat.
And as we just discussed with thermal noise, heat is the enemy.
But in this case, it's localized heat. The center of the glass where the laser is hitting it gets slightly warmer than the edges. And when glass heats up, 2 things happen. First, it physically expands, causing the flat surface to bulge outward.
A physical bump.
Yes. And simultaneously, the refractive index of the silica changes with temperature. This combined effect is known as thermal lensing.
So the mirror accidentally turns itself into a magnifying glass.
Exactly. It distorts the perfect wavefront of the laser beam. And when you distort the wavefront, you completely destroy the contrast of the interference pattern when the sheet eventually recombines at the detector.
Your signal just dissolves into a soup of noise.
Yes. The physical perfection of the mirror is literally the only thing keeping the physics of the measurement intact. It is the difference between measuring the collision of 2 black holes a billion light years away and just measuring the heat of your own laser beam melting a piece of glass.
That is so wild. And that thermal problem becomes exponentially more difficult to manage when you look at the sheer amount of light they're pumping into this system.
Which brings us to the ruler itself, the laser.
Right. We have our perfectly isolated, super polished 40-kilogram monolithic glass mirrors. Now we need the light. Advanced LIGO made a massive, fundamental leap in laser power.
We really cranked it up.
They shifted to a solid-state amplifier setup that pushes the initial input power up to somewhere between 125 and 200 watts. And during their third observing run, known as O3, they were routinely injecting around 40 to 50 watts of that available power into the interferometer.
Which is vastly more power than initial LIGO used.
Right, but why? We just talked about how the laser literally acts like wind, bucketing the mirror and creating radiation pressure noise. We had to make the mirrors 40 kilograms just to survive the push of the light.
Yep.
So why on earth would they intentionally crank the dial on the laser and make the wind stronger?
Because it solves the exact opposite quantum problem, shot noise.
Okay, shot noise.
Radiation pressure limits the detector's sensitivity at low frequencies, where the slow buffeting of the mirror masks the slow rumbling of heavy black holes. But at high frequencies above 100 Hz, where you listen for the rapid, high-pitched chirp of colliding neutron stars, the detector is fundamentally limited by shot noise.
I've always visualized shot noise like rain falling on a tin roof.
That's a really good analogy, actually.
Like, if you have a very light, misty drizzle,
Yeah.
you hear individual distinct pings as each raindrop hits the metal. The sound is highly variable, it's choppy. You can't get a good sense of the average rate of rainfall because the statistical fluctuation from 1 second to the next is so erratic.
That is exactly the right way to visualize the quantum uncertainty here. In the detector, the raindrops are the individual photons hitting the photodetector at the very end of the line. Shot noise is the quantum uncertainty in those photon counting statistics.
If you have a low-powered laser.
You don't have enough photons. The interference fringe, the light and dark pattern that dictates the measurement is grainy. It's uncertain.
The detector is struggling to tell the difference between a dark fringe getting slightly lighter because of a gravitational wave, or just because a random clump of photons happen to arrive at the same time.
Precisely. But if it's pouring rain, a torrential downpour, those individual pings on the tin roof blur into a smooth, continuous, predictable roar.
The statistical variation as a percentage of the total noise drops dramatically.
Exactly. By cranking up the laser power, you are increasing the downpour of photons. More photons mean better statistics. The quantum fuzziness smooths out, the interference fringes become razor sharp, and the shot noise drops drastically.
It makes your ruler vastly more precise at high frequencies.
It does. But no matter how sharp you make the ruler, a 4-kilometer arm just isn't long enough to measure a gravitational wave, is it?
Right, because if the laser light just traveled down the 4-kilometer arm, bounced off the mirror once, and came right back, The physical phase shift caused by the passing gravitational wave would be far too small to register, even with 50 watts of power and super polished glass.
It just wouldn't be enough distance.
And this is where the optical architecture gets incredibly clever with Fabry-Perot cavities. The 4-kilometer arms of the interferometer aren't just empty vacuum tubes with a mirror at the end. They have a partially reflecting mirror placed at the very start of the arm called the input test mass, and a fully reflecting mirror at the far end, the end test mass.
Together, these two mirrors form a resonant cavity.
The light enters the arm through the partially reflecting input mass,